housekeeping type things.
Recording in progress.
Just want to do a couple of housekeeping things first. If you have a presentation today and have not uploaded your slides to the folder, please do it as soon as humanly possible. I don't want to be a jerk and call out names, but there are several that are between around 11 o'clock today and 2 o'clock today that haven't put their presentations up. And if you don't have the link to the folder, let me know and I'll send it to you again. I think that's about it for now with that. So I will turn the floor over to Gopal. He's chairing the next session. Gopal, it's all yours. Actually, I lied. I have one more thing. I want to give a huge shout out to the OSTI modeling support staff at our contract STC. They're doing notes remotely for this because we didn't have travel money to bring them down, and they're doing a phenomenal job. So thank you guys. Appreciate it.
Morning all, and welcome to the session, an important session in HFIP. And I wouldn't stand between the session, and I'm not going to give a big introduction, except it's a little emotional on this. I still remember the time we transitioned HWARF in 2007, and it was probably the transition was between me and Vijay. That's how we started probably. And then as we went to 2012, it expanded, and it was EMC, AOML, and then Sujin was involved. Vijay and other people were involved, and I'm able to right now I'm able to see a huge team involved, and I know how much of work has gone into this. 2 models getting transitioned potentially into operations this year, next year. We all know how difficult it is, and I've been sitting in many of the meetings with both the EMC team as well as the AOML team, and more than the time, what I'm seeing here is a passion in getting the science into operations, and I would give full credits to each member of this team. And before we start this session, I would, if possible, I would give a good hand shout to everyone for even making it, because last December we didn't even have a moving nest, if I remember right. And now we have a model running, and so many runs have been made. Statistics being have started coming out. It can't happen without people working 24/7, all of them. So full credits to them. And this session is going to be more oriented towards what's happening with the HAFS, although an update, Zach will give an update on HWARF, but it's going to be what we want to focus more the first half on what is our next generation, how is HAFS doing? Whether we can go into operations with this model, which I believe the results show that. And then what are the challenges that we are going to face? That's going to be in the end of this session. There'll be 40 minutes of discussions, 45. And then we'll go to the next generation effort and what do we want to put as real time next year, which will come to consensus on what we want to do. So that's the summary of the session in general. And I would welcome Zach, who is leading this effort to, yeah, he's the transition man. So it's all yours, Zach. Go ahead.
Good morning. Thanks, Gopal, for the introduction. And my name is Zach Zhang, and I'm the hurricane modeling team at EMC. So today I'm going to talk about the upgrade. This is usually our HFIP annual report. So I'm going to talk about the upgrade and performance of both operational model and our experiment model in 2022 hurricane season. So in 2022 hurricane season, we did several experimental, like operational and also experimental modeling experiments. So basically in 2022, we do not have, there's no operational hurricane system upgrades. We were focusing on the HAFS development. But we did successfully transition the operational both HWARF and HMount from Cray to WCOS2, and also we upgraded the scripting system from Python 2 to Python 3. So that's what we did for the operational system, and we do 2 configuration of experimental HAFS experiment. We call it 0.3A and S, and you will hear more details in the next few talks. So this is 2 real-time experiments. I will also touch upon the HAFS-based ensemble real-time experiment, which is not official because we don't have the resources, but we did it anyway. And I will talk about show some results, and also I will summarize what we are going to work on for the first version, HAFS version 1 development activities. So this is basically showing the statistics of track and intensity forecast errors performance for 3 regional models and also the GFS model, global models, and for all 3 major global basins. And the top shows the track forecast and track verifications, and the bottom panel shows the intensity verifications. So if you can see it clearly, I mean, so the black line is the official forecast, indicator official forecast, and the blue is the GFS global model, and purple is the HFIP, and the green line is the HMON. And also I included the orange line is the COMS TC performance. And also I indicated, I mean, just for the intensity forecast, you can see HFIP performance much better, even better than the official forecast for the intensity forecast. So here just to summarize what we have, I just showed for the Atlantic Basin, North Atlantic basins, operational HFIP had the lowest intensity forecast errors compared to all the other models, especially after day 3, and even better than the official forecast. And also operational HMON performed both better than HFIP, both in track and intensity. And for the East Pacific, HMON did a very good job in the East Pacific, both in terms of both track and intensity forecast. For the West Pacific, the HFIP had the lowest intensity forecast errors at all forecast lead time compared to other models. And also the forecast errors actually comparable with the JTWC forecast before day 4. So GFS had the lowest track forecast in the West Pacific basins. So I'm going to switch gear to talk about the 2 real-time HAFS experiments. So this slide shows you the 2 configurations. The red line, basically the domain configurations are the same between the 2, and I indicated the difference in red. So basically the radiation calling steps are different, and also the microphysics, the configuration uses different microphysics, and HAFS A uses JFDR microphysics, and HAFS S uses Thomson microphysics. And also there's some difference in the vortex initialization. How do we initialize the vortex? There's differences. That's 3 major difference between the 2 configurations. So in terms of performance, we did 2-year retrospectrons from 2020 and 2021, and plus we did the real-time experiment up. This is the statistics verifications up to last week. So does not include the current ongoing hurricanes. So what you can see here, this is 3-year retrospectrons. The top 2 panels shows the arrow in the aerospace, and the bottom shows in the scale space comparing with current operational HFIP. What you can see here is both HAFS configuration improve the track forecast over HFIP around 15%. And in terms of intensity forecast, it's kind of mixed, especially for HAFS S. It's very comparable with the HFIP, but HAFS A configuration the impact is kind of neutral compared to HFIP, but somewhat degraded after day 3. So we are still working on the data simulation aspect and also model, try to improve the model for physics schemes. So this is for the EastPack, same verification for the EastPack. You can see this somewhat similar stories, improve the track forecasts about 15% for both configurations, and intensity forecast even, I mean, both intensity forecasts are improved from new chip at the earlier forecast time, but improved over at the later forecast time. This is 3-year recharge spectrum for the EastPack. And like 2 weeks or probably 2 or 3 weeks ago, we found a bug in the ocean coupling, the momentum fix exchange between the atmospheric and ocean coupling, and we fixed the issues. So that this ocean bug fix did not include in the stats I just showed previously. So we tried to rerun some of the storms to see the impact, if the impact of these bugs. What I'm showing here is after we fix the bug, we have an additional improvement over the intensity forecast at almost all the forecast lead time. So we are going to rerun more cases to see if this impact, the positive impact, is sustainable. It's not working. How do I should move? Okay, yeah. There's 2 of them. Okay, so this is the HAFS-based ensemble forecast real-time experiment. It's not official because we don't have the resources, but we did it. We found some resources on here, so we did it. So basically, the configuration is the same or similar to the last year, except this year we only run 11 perturbed ensemble members plus 1 control one. And all the configurations are similar to the HAFS-A configurations. So what you can see, this stats showing the verifications compared with its own control models, which is unperturbed ensemble members. So what you can see that for the intensity forecast, the check forecast, it's the average ensemble mean is kind of neutral impact compared to its undeterministic models. But when you look at the ensemble mean, you have like 20% improvement comparing the ensemble mean versus its only deterministic model. Even I also put some HAFS-A verifications. It's even beating the high resolution on HAFS-A configurations. And in the most right side, you can see I listed the both multi-model ensembles and also the single model ensembles we are running. What you can see, the point here is that both system has the left side track bias. It's even all with all the ensemble members. So this is my last slide. So we are trying to working towards the first version of HAFS. On top of we already showed HAFS v0.3a or S. So basically we are going to merge the latest HAFS UFS weather models into HAFS, and also we are going to implement the ESG grade with some dynamic tuning. And the blue in text indicates this task is already done. And also we are going to tune the model physics to improve to further improve the intensity forecast. And we are going to optimize the threshold for the vortex tunization. And another experiment we are trying to do is to do the 4D ENVA transition, to do some 4D ENVA experiment to try to mitigate the initial spin down, spin up issues. And also we are adding more observation data like enhanced GOES-R AMB data, and also update the GOES 18 and NOAA 22 data. That's two additional observations. And also we are working on the NOAA MP land surface model with updated vegetation type. And also another area we're working on is the unified gravity wave drag. See if we can implement these schemes into the moving nest. And also ocean coupling bug fix I already talked about, it's already fixed, and the company we have to comply with NCO code standard. And another thing, the big issue we are trying to resolve is the model instability. We see like about 1% model failure rate. We are trying to address these issues. And also the JTWC basins, we have to do some physics tuning and also do the test and evaluations. And another impact we are trying to do, because I guess later in this, sometime in December, GFS is going to upgrade to 16.3. We are trying to do some experiment to see the impact. And finally, we are going to do 3-year experiment for the finalized version. We are going to freeze the version in earlier January next year. I guess that's all I have. I will take any questions. Thank you.
Any questions? And if there is something from a message or something like that, we can. Okay. Yeah. You can see your
my name is Yuxin Wang from University of Hawaii. So I heard several presentations and talk about the left bias of the track. So I'm wondering whether the track is northward track or the westward track and have the left bias. That's very important because you want to look at that's the internal dynamics or the environmental effects.
Okay, but so we actually check the status in like whole years last year. They have the bias, I mean, left side bias in general. And the left side bias, we particularly talk about is Ian, which is going north.
Okay, that makes sense because if the track is northward track, you have a left bias, that's mainly probably the size is a very important factor. The size is too large. That's the Rossby wave, we have a larger phase space.
That's right. And also, I mean, yeah, we had some experiment. I mean, we did some like microphysics because we have two configurations. One use JFDR microphysics and one use this Thompson microphysics. Thompson microphysics seems have more left side bias.
Yeah, that makes sense because the Thompson scheme have the more stratiform clouds. Stratiform clouds mostly cause the size increase. If you have a larger size, often northward track, you have the westward bias. That's the left bias. Maybe to look at the details. And
yeah.
Yeah. Okay. Thank you.
Hi, this is Levi Cowan, JTWC. You teed me up so nicely with that bullet point regarding JTWC basins and the physics tuning. Are you implying that there will be different physics for different basins? And if so, what changes were you thinking would be necessary for, say, the Western Pacific, Indian Ocean, et cetera?
Okay, so yeah, that's a good question. Actually, we did some experiment for the West Pacific already, and we find we're going to run only HAFS A in the West Pacific, by the way. Okay, so this is the only configuration, and we did some experiment. We found we improved the track forecast, but there's a large degradation in the intensity. So we are thinking probably we will use different physics, like we're going to tune the physics in the West Pacific. That's what we did for the operational HWRF.
Okay, I'm not sure I was aware that HWRF had different physics per basin, but that's interesting. Is there a publication or reference that I could look up that has details on that particular part?
In current HWRF?
On the HAFS work for HAFS A. And
HAFS A, we have not, I mean, we have not decided like how we tune the physics yet.
Okay, thank you.
Yeah, in the interest of time, probably we have another session where we can discuss all this as well. Yeah. Yeah, we'll move on to the next presentation. It's going to be by Ben Lu on HAFS A and Jung Hong Shin. Go ahead.
Yeah, good morning, everyone. Today I'm gonna basically report what we have been doing or what we did for HAFS version 0.3 development. And also this configuration is used in this year's HAFS A real-time shipment. So this version is basically featured with moving nest and moving nest company with Ocean. Also, we have intercode data simulation and vortex initialization capabilities. So, before I get started, I want to acknowledge my co-authors here, a lot of them from EMC, from our AOML collaborators, also from NCAR ESMF. I also want to mention this is definitely a collaborative effort of the whole UFS hurricane application team. So without all these efforts, like Gopal mentioned, this will not be possible. So I don't think I need any introduction of HAFS to this HFIP community. So I just want to draw your attention here. Basically, on the right two panels are the 2021 HAFS A configuration real-time experiment performance for Atlantic Basin. You can see at that moment, look at the cyanide there. For the track, basically we are better than HWolf, and we are very close to GFS, probably partially beat GFS already last year. However, if you look at the intensity, longer focus time, it's still it's already better than HWolf at that moment. And the problem is the short forecast lead time. It is still kind of behind the HWolf. We know the reason because at that moment we do not have a moving nest. We do not have vortex initialization intercode data simulation yet. So those three aspects are the major goal or objectives for this version of HAFS development for 2022. So this is the HAFS version 0.3a configuration. Zach just talked about it. I will not repeat all of them. I just want to highlight a few things. As I just mentioned, we do have the moving nest capability, which we have a 6 kilometer parental domain with a 2 kilometer moving nest. I want to mention this is a great effort, collaboration, led by AOML, HRD, and EMC, also collaborating with GFDL and ESMF team. So we have this moving nest capability. We also enabled the coupling with the moving nest domain. And on top of that, I just want to mention we have the intercode vortex initialization data simulation capability for this new version. Another thing I don't want to mention is we did increase the HICON domain as well. You can see this HICON domain in blue here, which is much larger. Basically covers both North Atlantic Basin and the Eastern Pacific Basin right now. So just one slide highlights for the vortex initialization and data simulation. This one is a vortex initialization. Basically, this technique is inherited from HWolf, HMOM, and we did have some modernization of the whole package for vortex initialization. And we also have the development from Yonghui here. He developed the HAFS tool, which can do a different domain interpolation, merging, and mapping for the FE3 restart files. Those are crucial for us to do the vortex initialization as well as data simulation, actually. Again, for vortex initialization, basically we're trying to separate the storm environment from GFS, get the storm perturbation from previous 6-hour forecast, and then do the vortex adjustment relocation. And these 4 panels shows here just, you can see there are some changes near the storm region. Outside storm, we go back to GFS. Okay, this slide basically shows you the data simulation. Again, highlights something. We are basically using 3-hourly FGAT capability, using 3D EMWAD, using GDAS ensemble members for covariance. And we are assimilating basically all the observational types assimilated by HWolf, GFS, GDAS. Just one in the middle, of the slides showing you their HAFS A workflow, basically 3D EMR capability. Just want to mention maybe one thing here. For the red lines over there, basically are those HAFS forecasts with data simulation and vortex visualization. But the green lines is basically code stuff on JFS. You can definitely notice the huge differences at the issue time. So the vortex visualization data simulation does help initial intensity forecast. This is basically before kickoff the real-time experiment, we actually run this configuration for the past 2 years, 2020 and 2021. This is the performance for Atlantic Basin. You can see as shown in Zach's slides as well, we definitely have consistent track improvements for the intensity. It's a kind of overall mix with HFIP. And if you look at the earlier guidance performance skill, you can see, again, 10% improvements in track, neutral to maybe overall positive for the intensity. And then with that, we actually kick it off for this hurricane season. This is the model performance for the Eastern Pacific Basin from 1E to 19E, basically. Again, showing you here, the orange line is the HAFS A configuration real-time performance. You can see track improvements definitely. Intensity also beats HWOF for almost all lead times. I think it's also better than GFS as well. Excuse me. And then coming back to the Atlantic Basin, as Zach mentioned, we do have their momentum flags coupling back fix. So their cyan color is before the fix and the orange color is after fix. So basically, Zach already showed after fix, we get some additional improvements for both track and intensity. And then moving forward, I will just focus on the back fix version, which we call it HF3C. So this is a HF3C performance for their Atlantic Basin. Again, track overall better than HWOF and JFS. Shorter focusing time, you can see we are even or basically similar performance as HWOF. There are some issues for the longer focusing time and intensity. I think that's also shown in Zach's performance. We're gonna have more discussion on that part. And highlights a few storms for this year in Los Atlantic Basin. This is a forecast for Hurricane Fiona. Overall, you can see for the track, HAFS A is doing, HAFS C here, which is seen as HAFS A, is doing very good job in terms of track forecast. But intensity, we are behind the HWOF at the day 4 and day 5. But before day 3, it's basically the same as HWOF. You can see the problem is actually for Fiona, we have a few cycles. Earlier cycles of HAFS 3A or 3C got a very large left side track bias. That actually caused the intensity, weak intensity error as well. So a lot of those intensity error are probably tied with those track forecasts. This is one specific forecast cycle for Fiona. And you can see for this specific cycle, the HAFS is doing a great job in both intensity and track. And then we have this comparison, HAFS simulated 2 kilometer level of wind compared with the TDR observations. So they got a very similar pattern here. And I'm showing you this is basically an animation of this forecast cycle, the large scale flow, and then the storm scale reflectivity and the wind distribution. Another storm here, which is EM. Again, track, we are actually better than HWOF and JFS. Intensity-wise, before day 2 is basically very close to JFS, to HWOF, better than JFS. But after day 2 is again behind HWOF in this for this storm. For the track, you can notice HAFS 3A or 3C has a smaller left side track bias, better than HWOF. Also, I think it's better than JFS as well. This is also a specific cycle for Hurricane EM. Again, the TDR observation comparison for the wind distribution. Also, I'm showing you here a mid-level humidity distribution as well as the surface flux LC flux distribution near the storm region. Moving on, I just want to highlight a few things here for the ocean coupling. I know Hans-Hugo will have a great talk this afternoon. Just showing you here the SST distribution and the ocean heat content distribution at forecast hour 18. For this specific cycle here, I think our colleagues, Maria, also come up with some comparison with the drifter observed surface pressure. So you can see HAFS 3C actually did a very good job for the surface pressure evolution for this at this site. And actually, John also did a great comparison between HAFS HICON coupled sea surface temperature and up ocean temperature structure against the AXPT observations. So you probably can notice the observed SST is pretty good, well aligned with the observations. Also, the up ocean temperature profile is also very close to the observations, which is in black. So this is the combined performance for both Atlantic Basin and the East Pacific Basin. Added them together, actually, you can see we do see consistent track improvements. Also, their intensity performance is kind of neutral overall for two basins. I also want to draw your attention, if you look at the central pressure error, is actually better than H12. The wind pressure relationships also slightly better than H12 as well. So this is, I think, my last slide. Basically, Zach already mentioned we are continue working on improve the HAFS configuration, try to come up with the baseline configuration for HAFS version 1. We will further optimize in the model dynamics, physics, DA coupling, all perspectives. We basically have another 2 months also to finalize HAFS version 1. So it's still a lot of work to do. But I just show you 2 panels here. This is a pre-baseline configuration. You probably just pay attention to the blue line over there. With this version, we have 3 changes here. We are using ESG grid, latest HAFS package, and then we are also improved the numerical instability. So with these changes, you can see we get additional track improvements as well as minor improvements in their intensity. So with that, I think I can stop here. If I have time, I can.
I think we can entertain one question probably, and then we'll come back. Okay.
It's Frank Marks, HRD. I'm concerned that we're thinking about this track left error is due to physics. I want to put on the table initialization. Noticed a lot of those left errors where windstorms are weak. There's a lot of uncertainty in the center. Having flown in a lot of those storms at those early times, there's a low-level center that's totally different than a mid-level center, and they all evolve. If you're initializing on the surface center and it's a very tilted vortex, I don't know what you're doing to the dynamics. So I think we need to consider that as well as Yu Qing's comment.
Agreed. I think these are great comments and suggestions. At this moment, we are actually doing some sensitivity tests. Some of them turn off vortex initialization, turn off DA. We keep only say cold start from JFS, but we still see those track biases even when running the cold start. So I think these are very challenging things we need to tackle on.
I think till the lunchtime, I think this discussion should continue because we are in an IOC year and we need a lot of inputs from here on. So we'll go to the next presentation by Andy and Gus on HAFS. Yes, that's another one which is going to be implemented, I think.
All right, good morning, everyone. Thank you all for coming. So yeah, I'm going to talk about the other configuration of HAFS that was run this summer, HAFS 0.3S. So I'd like to thank all of our mini AOML, EMC, and GFDL collaborators, all who have contributed to helping set this up, running things. Tim got a new tracker running, and so just appreciate everyone's help in getting this experiment running. So this configuration, it's similar in design to the HAFS-A with the storm-centric moving nest that Bill designed. We're using that NHC HICOM domain, so and this 6 kilometer static outer nest. So sort of similar to HAFS-A in that regard. 81 vertical levels using the scale-aware SAS convective scheme. Some of the differences with HAFS-A, we used a modified version of the boundary layer scheme that we've tested based on some work that Xiaomin Shen and I have done. And he has some, we have some papers on that some of which are out or coming, and looking at some improvements to that for hurricane environments. This version also used the Thompson microphysics. So that's one key difference that in these two versions of HAFS. And also we did have one initialization difference in that we only turned on the vortex modification part of the initialization for cases where the storm was at least 30 meters per second. So basically just above hurricane strength. So in terms of overall track skill in the Atlantic, these graphics show on top the error, on the bottom is the skill, and in the middle is consistency metrics. So this is from some of Sarah Ditchek's work, which is really nice. Jason talked about some of this yesterday, kind of gets at, are these improvements in absolute error that we're seeing, are they consistent or are they robust? So we have both versions of HAFS. So our version that I'm talking about here, HAFS-A, is in red, and the skill and kind of any improvement or degradation is shown relative to HWRF as our baseline. So for track in the North Atlantic this year, you see the HAFS-S was doing well relative to HWRF. We saw consistent improvement, in some of the medium lead times. So maybe some early errors that kind of point to a need for continuing to improve what we're doing for initialization. But obviously the absolute error is pretty small there. Next slide. I guess I'll just answer myself. So for the East Pacific, even its tracks even better. HAFS, as you'll see with intensity, HAFS did very well out in the East Pacific. HAFS-S was the best performer, and even with a pretty robust sample, and you see very consistent improvement relative to HWRF and even HMOD, especially as we go to longer lead time. So that was definitely an encouraging result, up to 30% improvement at day 5. So the concern, and Ben and Zach both addressed this also, was the longer term intensity in the Atlantic, where we saw degradation relative to HWRF up to 20 to 30%. And that was consistent, as you see in the middle panel there, based on that metric. And you see that in the early lead times out to about day 2 to 3, it's really not that bad. It's mostly due to this, at least for HAFS-S, due to a negative bias at longer lead times. You see that on the bottom right. Kind of a similar bias characteristic to HMON. And I think Ben mentioned Fiona. That was one case that we saw was also problematic for HAFS-S. And so we're actively trying to diagnose what's going on with that. For the East Pacific, however, intensity was quite good. We sort of had, again, the East Pacific overall HAFS performed really well. There was a kind of a neutral out to about day 3, 4, but then days 4 to 5, HAFS-S did quite well relative to HWRF, up to 20 to 30% improvement, and it was well calibrated. You see on the bottom right, the bias overall was near 0. Obviously, some above and below that in individual cases, but we didn't see that positive bias like HWRF had. So well calibrated, for the East Pacific, and for track overall, it's just mainly that Atlantic long-term intensity this year. Although as some of the 3-year samples showed, maybe it's a little bit more neutral overall. One of the other interesting things you can do with verification, and this is something nice that in Sarah's package, is looking at this PPC metric, which is the percentage point contribution of each storm to the relative skill. So I won't get into all the details. There's a lot of numbers here. Basically, I wanted to highlight that for the Atlantic, at least, Danielle and then some Ian cycles were kind of the two that we did see some issues in track, and I'll talk about Ian in a minute. For intensity, Earl and Fiona were the two big ones that were problematic. And Earl was too strong, or Fiona was too weak, kind of in a similar region. So those two cases are sort of what we need to explore in more detail for this year. And I think some of those were already discussed yesterday and kind of in the challenging cases session. So go back and look at those slides. For these specific, looking at these individual cases, you can see early in the season, Celia 03E was a big one that contributed very strongly to both the positive track and intensity skill. It was a long-lived storm, so it was contributing pretty strongly to that overall consistent composite improvement you saw. K12E was also there. Interestingly, Bonnie was sort of a negative. That was one that crossed over. So maybe there were some terrain things. Zach mentioned we've had some some things with terrain we're trying to address, because it was near land. So that could be part of what was going on with that one. So I wanted to spend most of the rest of the talk looking at Hurricane Ian, which was obviously one of the most well-known storms this year, very high impact. One of the things we noticed with HAFS is that early on, some of the tracks had some of the cycles had a track that was too far left. The peak intensity was generally very well predicted. I remember, seeing HAFS predicting a storm, basically approaching Category 5 in the Gulf, a couple of days out, and I was like, I hope this is overdoing it, and it turns out it really wasn't for the most part. And if you look at the overall performance, it's pretty much all the GFS-based guidance was similar, I'd say, in terms of track and intensity. Some different bias characteristics. You can see, again, for this case, HAFS was kind of similar to what we saw with HMON. Maybe a little bit of a weak bias related to that early left bias and track, but it was pretty good overall. And what was interesting for Ian was, again, you can take that PPC metric and look at how each cycle and each forecast hour contributed to the overall skill. And this kind of gets to one of Frank's points that he made in that question he just asked Ben, is that the early cycles for Ian, the first 4 or 5 cycles after Genesis were really where we saw this leftward track degradation. After about the 25th at 0Z, you can see all those greens. We actually saw, consistent improvement relative to HWRF. The intensity was sort of a mixed bag, nothing too, I would say nothing too high or low there, fine overall. But in track, actually, once we got past that initial sort of, maybe it was the vortex alignment, or, the other thing that I noticed talking to Sarah was that 25th at 0Z was when we started to get consistent TDR data in the storm. Why that only affected HAFS, if that's the case, I'm not sure. But it's clear that, like Frank said, some of this, whether it's how we're initializing or just the processes in these early stage storms, we're not quite getting all of those things correctly. And certainly that affected the synoptics as well. Hurricane Ian, I have here 200 millibar potential vorticity from HAFS A on the left, which is a little bit further right, more correct, but still a little too far left compared to the analysis. HAFS S is in the middle. You could see that both versions of HAFS were not amplified enough with a trough over the eastern U.S. That's kind of a common problem for GFS-based guidance. They tend to not get the western ridge and east coast trough amplified enough. It's a well-known issue that showed itself here. But even in between the two versions of HAFS, there were some subtle differences in sort of the tail of the trough extending over the Gulf of Mexico, where it was further north and east in HAFS A, closer to the storm, helping to sort of pull it off to the right. But of course, the question, that still needs to be addressed is, was this truly a synoptic difference, or was this just a storm scale difference early based on how much precipitation or what kind of precipitation you had, and then how that diabatic heating maybe eroded the PV? So it's sort of a chicken and egg problem, but clearly there was some differences in how the small scales were feeding back up to the large scales here. And like I said, it wasn't a huge error overall, but certainly in terms of a communications and impacts perspective, it's something that needs to be addressed. But one positive for Ian, we did see some of the structure processes well predicted, once we got that track right. So on the top is the HAFS forecast of reflectivity, the low level wind field, and then an azimuthal mean of wind. On the bottom is one of the P3 flights. This is one I was on where we were observing a double eye wall. And you can see that HAFS actually did a pretty good job showing, not perfectly, but sort of that double peak, and same thing in reflectivity. So it got a lot of the structural features that were observed pretty well once we got, we're able to lock on to the correct track in the Southeast Gulf of Mexico. So just to summarize this year's performance, HAFS S performed better than HWRF in the Atlantic, any specific for track. Intensity, we saw a mixed bag, some quite solid in the East Pacific long range, but some degradation long range in the North Atlantic. Some of that's a little bit more smoothed out in the 3-year sample that Zach showed. The Ian case, it showed some early track bias due to those early stage processes, but then also early forecasts within about 3 days of landfall and accurate RI prediction. And certainly that's, an improvement, thinking about like going back like 10 years or something like that. So obviously there is still a lot of things that we still need to finalize and improve. And we'll talk about some of this in the discussion later. There's coupling, there's that little bug fix that we've been testing. It doesn't really seem to have a huge impact, but definitely in some cases. Nesting, we're still working out some things with terrain and optimizing that. Data assimilation and how we initialize, clearly there's some things we can do better there, and we'll talk about that. And physics, how do we Thompson, that's a fairly new thing to try to implement this in a hurricane model. So is that going to be a viable option? The results seem pretty good this year, but, optimizing that and along with the PBL and exactly what we want to do with physics, we're, scheming some sensitivity tests to see what our optimal final configuration is going to be. So I will take any questions.
Thanks, Andy. And any questions? I think this time I'll start with remote participant. I think there was a question from Go from GFDL, and that was relevant to both the versions of the model.
Sure.
He has asked about the diffusion on the model. Kun, do you want to go ahead and ask your question?
Oh, yeah, thank you, Gopal. The question actually has been addressed online through the chat box.
What did he say? What was the question? Can you read it?
Can you repeat it? Oh, okay.
Yeah, question was related to flex prediction. He mentioned that in his sum, there are some flex in model diffusion with the ESP grade. So I was wondering what's be made. Yeah.
Oh yeah. I'm not sure what the plans are for that. I mean, for this version of HAFS, we're using, like the less diffusive tracer advection scheme, that you're well aware with. But I haven't heard of any plans to tune that, but maybe the next or the other speaker would have more information on that.
Yeah. Thank you. And that may be one of the discussions that we want to talk about actually. And with that, if there is no other question, probably we'll move on to John Martinez, what he finds from NHC verifications. Go ahead, John.
All right. Good morning, everyone. I have a presentation today where I'm going to be talking about some of the impacts of the HAFS models on the consensus models that the National Hurricane Center uses. And I have a nice infrared image here of subtropical storm Nicole from last night, just to give some context to Brad's discussion earlier. So we do see a lot of improvement in the convection from overnight. Okay, so I have 3 parts to this presentation here, and I know there's been a lot of buzz about each of these components to the HAFS model. So yeah, I'll be talking about the track and intensity verifications. And for the wind radii, I'm going to focus on the radius of gale force winds, so R34, just for the sake of time. And then I'm going to talk about the highlights from R50 and R64, but they generally follow the same theme. So I'm happy to share those results with anybody who wants to see them. A brief aside before I begin here. So HAFS will have implications for several of the guidance products at the National Hurricane Center. Again, I'm going to be talking about the consensus models, but we also have HICA, DTOPS, and NNIC. And so each of these guidance products are going to be part of the guidance suite production code that's delivered next year. So when the HAFS retrospectives are made available, we have to test the impacts on each of these products before HAFS can get implemented. So that's just a heads up that there's a lot of work ahead of us. And that seems to be a common theme for each of the teams here. So a brief introduction here for the verification design. We're doing a homogeneous verification. So this requires that the model has a prediction present. Each of the models has a prediction present at each of the lead times. Thanks to Gus, we were able to look at the HAFS tracker files from 2020 through 2022. I've only included up through AL14 and EP19, so a couple storms missing here, but a pretty comprehensive assessment for this year. And then the operational interpolator offsets are implemented here, and Ben did some work to determine the optimal offsets for HAFS, and we have that listed at 6 and 30 hours. Okay, jumping into the results here, looking first at the track verification. These slides are a little bit verbose, but for the sake of completeness, I'm listing the texts that are included in TVCN. So that's the track consensus model. It's the variable consensus with a minimum of 2 members. In the North Atlantic, we have 6 models, so only HWRF is going to be replaced. And I did a couple of tests where I replaced HWRF with either HAFS A or HAFS S. And so you see TVCA and TVCS correspondingly there. And then in the East Pack, both HWRF and HMON will be replaced. So we swap both of those models out with the HAFS models. For the results, I'm just going to be focusing on the mean absolute error and the relative skills. So in all of these slides, you'll see on the left column, the North Atlantic Basin, and on the right column, the East Pacific Basin. In this case, yeah, we see a great improvement for the consensus models by incorporating the HAFS models, roughly 5% at all lead times in the North Atlantic. Slightly mixed results in the Eastern Pacific, but we do see pretty good improvement at days 4 to 5. So we've been hearing a lot of discussion today about how the track improvements have been great for HAFS, and that skill improvement does translate into the consensus models pretty significantly for both basins. Looking at the along and cross-track biases, the HAFS models slightly reduce the along track and cross-track biases in the North Atlantic and East Pack at roughly all lead times. These improvements aren't major, but for the East Pack, it was interesting to note. So you could see in the gray lines there, I've also included the individual HAFS models. There's actually a slight right of track bias in the Eastern Pacific, and that might actually be offsetting some of the predominant left to track model bias that everybody's been talking about the past couple of days here. Okay, so thanks to Ben, he was able to whip up some quick work for HICA. I have a little bit of context here for the approach that he took. So we took a leave one out training method here. So all of the tropical cyclones are included in the training data, except the one that's being forecasted. And then Ben ran a few tests here. So the text with 3 effectively merge the HWRF and HMON retrospectives with HAFS. And so this assumption is that the models have a similar error characteristic. And then the texts that have 4 in them remove HWRF and HMON and only add the HAFS models from 2020 to 2021. So a little bit less stability there from the smaller sample size. So pulling up the results here, those texts that are merged with HWRF and HMON are shown in red and green. And you can see a slight improvement in the track skill when incorporating HAFS at all lead times, roughly 2 to 3%. And of course, you get a greater boost if you only use HAFS and you completely remove HWRF and HMON, but that's at the expense of consistency because the model or HICA loses its stability with those small sample sizes. So promising results for HICA when it comes to the track forecast. Here I have a quick summary. I'm just going to jump through this slide for the sake of time here. I'm going to bring it up at the end if anybody's curious what the overall results look like. So jumping into the intensity verification, we have, again, a variable consensus model with a minimum of 2 members. Now for IVCN, the North Atlantic and Eastern Pacific both have HWRF and HMON, so we're going to swap those out with the HAFS models. Again, in the top column here, or sorry, in the top row, I have the mean absolute error. Bottom row is relative skill. And so in green, we have the consensus models. And we see that the HAFS model slightly reduces the skill of IVCN in the North Atlantic Basin, and this is primarily evident at the longer lead times. Some of those reductions are up to 10%. In the Eastern Pacific, though, we see a slightly different story. We see a relative improvement in the intensity forecast skill by incorporating those HAFS models. It's about 2% for most of the lead times, and it's actually quite large at days 4 to 5, but that could be a sampling issue because the sample sizes get pretty small out there. And then there's a pretty small dip at day 3 in the skill, and this was also apparent in TVCN. Again, this could also be a sampling issue, but I saw some relative improvements at day 3 in those slides that were brought up earlier with the bug fixes. So I'm not sure if there's some magic going on at day 3 with the ocean coupling there. And then for the intensity bias, I think this was just touched on earlier by Andy. You get a slight reduction in the intensity bias in both basins. So that's a plus as well. Okay. And then I have the same methodology listed here for HICA. That's just for reference in case anybody wanted to read through it again. But for those text where we merge HAFS with the HWRF and HMON retrospectives. Those are the green and red again. Those actually show the poorest performance relative to just the HAFS models, but overall we're seeing a reduction in skill when we bring in the HAFS models into HICA. Okay, skipping this summary again, we move into the wind radii verification. So again, I'm just going to focus on R34 here. For context, RVCN is also a variable consensus model, but we have a minimum of 1 member. And then there are slightly different texts here because of the fact that we have different offsets relative to the track and intensity guidance. So all of the models have interpolator offsets of 6 and 18 hours. And then we're doing some tests because of the fact that RVCN only includes HWRF. We're gonna have a test where we replace HWRF with HAFS A and another one where we replace it with HAFS S. And I think I have, yeah, slightly different tech names, so sorry about that, but RVCA is for HAFS A and then RVCS is for HAFS S. So bringing either of those models into RVCN slightly degrades the skill of the R34 in the North Atlantic Basin. That's by about 2 to 8%. And then again, we're seeing a slightly different story in the Eastern Pacific where RVCN is improved and we're looking at 2 to 5% at day 0 to 3, slightly mixed in the longer lead times. Oops, not advancing. Thanks. And then looking at the biases here, HAFS has generally, so HAFS A has a generally comparable R34 small bias. You know, when we bring that into RVCN, HAFS S further amplifies that small bias. In the Eastern Pacific, we get slightly mixed results here, but we're actually seeing that the HAFS models produce a small bias in RVCN relative to the current large bias. So when we swap out those models, you get a slightly different bias compensation. Okay, next slide, please. I don't think it's advancing. Oh, there we go. Okay, so before I pull up the conclusion slide here, I just want to mention that this was a preliminary evaluation of the impacts on the consensus models. And we, of course, want to do a more comprehensive assessment. So distinguishing between weak and strong tropical cyclones and perhaps considering a better threshold, as Joe mentioned yesterday. Doing some regional verifications. So for example, in the Atlantic, isolating the MDR from the full basin. And then we could also look at cases in the East Pac based on that region where we really see that strong left to track bias that Brad mentioned yesterday. And then we want to look at cases where we have intensity forecasts with and without observations, and of course, RI versus non-RI cases. I think it will certainly be worthwhile based on Andy's presentation to identify some of the outlier cases that were contributing to a significant reduction in the skill from HAFS, because that's going to translate into a reduction, of course, in the skill from the consensus models. And so contingent upon the availability of the model fields, it would be great to diagnose or try to diagnose some of the sources of those errors in more detail. So it'd be great if we could collaborate on some of that work. And then, of course, we need to diagnose the downstream implications of incorporating, HAFS into the various consensus models, but primarily we're talking about DTOPS, HICA, and NIC here. So with that, I will pull up sorry, could you advance to the next one? Great, thank you. Here's an overall summary for those who were curious. These are the results that I pretty much breezed through for the sake of time, but yeah, I'm happy to take any questions.
We may have one question, probably I'll go to Mark and then we can come back to you.
Yeah, I think what you've shown is that there's still a lot of work to be done to get the consensus models and other downstream applications like AWIPS displays, National Blended models. And like the delivery time for our guidance suite code is February 15th, or when NHC has to deliver it. So it looks like there's kind of a mismatch of when we're going to get the retrospective runs and when all the code for the downstream applications has to be implemented. Is there any new updates on when you can actually get the retrospective runs? I think maybe Stephanie knows, but maybe there's a chance for a tweak in the NCO code in June-ish timeframe, but the majority of this work has to be done pretty soon.
You have a response to this, Zach?
So our current plan is like we freeze the code in earlier June and we start 3-year retrospective runs. Early January, yes, sorry, early January next year. And we're going to start 3-year retrospective runs. But I would suggest probably right now, we can provide, before that, we can probably provide some previews, I mean, before the when we freeze the code, but not the final version. We can provide some data for you to test it. And the expected, I mean, the earliest possible we can deliver the final results will be February still. I mean, probably middle of February. Yeah.
Yeah, John, this one, you say H-Wolf reduce the intensity scale for IVCN, the consensus model, 10%. Like, I'm just wondering how you weight HAFS into the consensus model?
Yeah, so maybe I should highlight that the text says up to 10%. That was roughly the worst. On average, it was a lot smaller than that. But in regards to how HAFS is weighted, it's evenly weighted among all of the consensus members. It's just a simple average.
Certain. Okay, thank you, John. So the very idea of the session was to give a big, more or less bird's eye view of what's going on, because things are happening so fast. So what we thought we could do is to give a brief kind of presentation and go over the outstanding issues. Basically, one we thought was physics and the issues. So we thought we'll have, before going into the discussions, I thought we can invite a couple of people to just present on part of DA and physics issue. I would invite Vigo. He's online. Vigo, can you go ahead with your brief presentation on, we'll get started with physics and DA.
Yeah,
and I know
yeah.
this is going to go on.
So, hello. Yeah, this one. So today, I will present some physics-related issues we found in 2022 HAFS real-time experiments. So in 2022 real-time experiments, HAFS was very successful, as presented in the talks this morning, particularly for tracker forecasters. But there are still challenges and issues. Here, I will focus on some possible physics-related issues. So next. Actually, we do not have answer yet. So we just want to listen to suggestions from all kind of experts here. Yeah. So actually, in terms of the verifications, both HAFS versions did a very good job in East Pack. But there are some concerns showed in North Atlantic and the West Pack basins. So here is for North Atlantic. So the first, the top left is the intensity error. You see after 2 days, the intensity error is much larger than HWolf and even larger than HMON. For the intensity bias, you see HAFS A is very close, very similar to HWolf, but for HAFS S, there are very large lactive bias after 2 days. In terms of the R34 size bias, you see HAFS A is very close to the HWolf, but HAFS S is a very lactive R34 bias. That means the storm is too small. So next. So this is for West Pack verification. So in terms of the intensity errors, you see the intense error is maybe 20 or 30% larger than HWolf for all lead time. And in terms of bias, it looks okay. Yeah, actually it's better than HWolf. In terms of R34, it's very similar to HWolf. except after 3 days, there's a bit larger bias. So next. So here the kind of summary of the issue from the verifications. So in terms of for the Westpac storms, we found the 20 to 30% larger error than HWRF at all lead time. So here the red one, that means we have some concerns or some issues. The green one, that means that's okay. Yeah. So for Westpac, we have some hypotheses. Yeah, we may need to tune the ocean, convection, and diffusion to address the larger error for all lead time. Yeah, but for Atlantic basins, for HAFS A, the absolute errors is 40 to 50% larger than HWRF after 2 days. So that's kind of difficult to address. So we need to listen suggestion from you. Yeah. So our hypothesis is maybe related to convection and macrophysics or radiation interaction, something like that, because this is a long-term error. For HAFS S, actually absolute error is very similar to HAFS A, that's too large after 2 days. And in terms of the mean intensity bias is 2 weeks after 2 days, and 10 or 15 loss, elective bias. But for size, it is too small. So here is I'm confused actually, right? The intensity is 2 weak, but the size is too small. So my suggestion is we need to check a low-level wind profiles. That maybe in PBR there may be too much diffusion or too less diffusion, something like that. So we need to take a look at that. So next. So next, this is kind of the classical issue, right? Older issue, right? RI issue. So here is the example. I choose the one cycle here. Right? The two versions have a very similar track. So you see the HAFS A failed to intensify in the beginning, but HAFS S intensify, but cannot sustain, cannot keep the big value. So that's I don't know what's the problem here. Yeah. So next is another issue, another RI issue example. Yeah. So in this example, HAFS A failed to intensify, but HAFS S, the same. Okay. Maybe something wrong here. Yeah, that's okay. Yeah. The next. Oh yeah. This one is next issue. Yeah. Next is another issue. Another example, HAFS A intensify too much, but HAFS S failed to intensify. So for this example, they have very similar track, but the two versions behave very different. Yeah. So next. So next is this a very classical issue, actually old issue, or that is underestimate the subgrid turbulence. Actually, we in the past years we did a lot of things to reduce the diffusion in the PBR in order to increase the intensity. But for Iowa area, you see here the left plots, the subgrid turbulence TKE is very small compared with large eddy simulation and compared with the radar observations. So we did some research on this one. So next. Look next. Oh yeah. So we did some research on this topic in H1. You see that we included the horizontal gradient of velocity and temperature, something like that, into the probabilizations. So we got some results very similar to the large eddy simulation and radar observations. So we will conduct this research into the HAFS in the future, maybe. So that's all what I have. Thank you.
Excellent. Can you go back to the concerns, and you had a slide. Can you go back to the previous slide, the previous one? Yeah, this can be placed. And any questions or any suggestions? I think we can start with Eugene and then go to Jaumin probably.
Yeah.
You had concerns about the size. Do you want to give your inputs?
Okay, I'm Eugene Wang for University of Hawaii again. And I'm actually the first time to attend the HFIP's annual meeting, and I'm very excited and I very appreciate the organization of the project. The national project is very successful in my personal impression. And and also I learned a lot of things from this meeting, because I'm from the academic side. We focus on the understanding instead of technical development. But I really learned something. For the academic side, we should emphasize and focus on more on the operational needs. So that's the major reason I came to join the meeting. Okay. So for the model development, I'm also modeler indeed, okay, at the beginning, but I also still continue to develop a model by myself, and also improvement in collaboration with some other groups. So for the HFIP, I'm wondering about why the model still uses the static vortex initialization so far. Okay, you say the sophisticated vortex initialization. Because the static vortex initialization is still the aligned in the vertical. That's what Frank just mentioned about. So in the environmental flow and in real world, we have the vertical wind shear and the movement of the storm. In particular, when the storm is weak and the storm matured, okay, in the vertical for several tens kilometers, and if you static vortex initialization always align in the vertical. So this avoid the interaction in the vertical direction of the vortex. Okay, so this may affect the intensity forecast and also structure and also the track. So I think this is the way to think about. Either now there's no enough time to consider any new scheme for the vortex initialization, but we should consider by this group, and whether we should go further to develop any dynamical initialization combined with data assimilation. Okay, so because the static vortex initialization should be retired, that's my personal opinion. Okay, so the dynamical initialization and combined with the data assimilation, I think this is the way we should go. In particular, you have the dynamical initialization, the vortex is adapted to the environment. Okay, if you have vertical wind shear and the vertical dynamical initialization can force the wave number one symmetry. That's what in natural in observation you can see. But the current vortex initialization probably doesn't fear any environmental effect like the asymmetrical structure of the storm. So that's one of the my concerns about the question why we don't consider these directions. Okay.
Actually, Eugene, it's little more advanced than the initialization which we are thinking about and which I have adopted from my idealized case from you, basically. So, yeah, this one is little advanced, I think. Yeah.
So I think there might be a little bit of misunderstanding. The vortex initialization provides the first guess for data simulation, right? So I just want to make sure you understand that it's not, and yes, you are correct that the fact that vortex initialization produces an upright coherent vortex, even as just the first guess for DA, is problematic. I have done, so there's two components. There's a relocation, right? And there's a vortex modification. The relocation you have to do, because if you don't do it, when you assimilate intercore data, it's a disaster. So at least with the 6 hour cycle, right? Six hours is just, you have to do some kind of relocation. The vortex modification. So I actually did a pretty comprehensive assessment of where it's helping us and where it's hurting us. And the current scheme, it's helping us when the intensity is changing. When the intensity is steady, the DA alone is with vortex relocation is better. But when the intensity is changing, the DA just can't keep up. Now, to your point about having a more advanced vortex initialization, I totally agree with you. I don't like what we're doing. It's just what we have, right? So I have I've played around with an idea of doing the vortex relocation within the context of GSI, of having, basically fake data or data from the previous 6-hour forecast and relocate that and then assimilate that to relocate your vortex within the DA or as a prep to the DA step. I was having problems with it. I think we need something else, more effective than what we're doing. But I have a talk on DA. We also just need better DA.
There is going to be, there is going to be a session in the afternoon on DA plus at the end of this, we are going to move on from physics to DA anyway. So your questions on physics is also welcome here, basically. And we want to, So with that, probably, you have.
I just want to quickly respond to the Eugene's comments. And actually, if you look at our plan for the after first implementation, we have a plan to upgrade the vortex initialization and work with the DA system. So that's in actually, if you look at yesterday's talk, we do have the plan to do the vortex initialization. And also, I have one comment on the WIGOS slides showing like we have a larger degradation. HAFS, we have a larger degradation after day 2 or day 3. I mean, this actually partially fixed because when there is sampling size, it's the small size. In the Atlantic season this year, we have a very small sample size. And secondly, we fixed the ocean bug. We have an ocean bug fix. And what he's showing here is not, the ocean bug fix is not included. So that's my comment.
Thanks, Zach. Any other comments on physics before we move on to, Xiaomen, you have
actually, I have a question just now about the page summarize the HAFS A and HAFS S performance. Yeah, it's very notable, like especially the R34 issue. Yeah, I just want to mention like for HAFS S, I include an experimental like a new feature in the PBL, basically to address the double counting issue for the shallow cumulus and also the PBL. And right now it looks like it's a little bit more aggressive. But meanwhile, also like team is recently upgrade the tracker. So that probably can address the tracker issue a little bit, because before we upgrade the tracker early this season. So actually the R34 for both HAFS is pretty good, especially HAFS S. So you have a very good like R34 performance. So that's very sensitive to the tracker as well. And meanwhile, like for this, like some like high weak bias actually for the HAFS S, some early cycles. So those kind of related to the PBL as well. So yeah, we are going to have some more tests about that. So that's just a few comments. And so meanwhile, like, so do you have comments like to continue or just?
Another part of physics that you can go ahead and then we can set the questions.
Yeah, so I will try to introduce the TC-PBL option in the HAFS. So that's an option recently available thanks to Bing and Trenchi from EMC to help make this just a one nameless variable to turn on, turn off. So it's very convenient to use that. And so basically we use that to switch the PBL physics for hurricane applications. While the name is TC-PBL, but I just want to emphasize that it's probably have more broad application more than hurricane conditions, because it does not supposedly not degrade the non-hurricane performance. I will introduce why is that. And so let's take a look about the PBL scheme used in the HAFS. So it's EMF TKE scheme. So recently upgraded the GFS and the HAFS, and it's designed for convective modular or low wind conditions, not really supposed to be hurricane applications. So we just take a step to this issue, evaluate the PBL scheme in hurricane conditions. So right now the plot just give the example about the 35 experiment. Basically the 10-meter wind speed is 35 meters per second. And we develop a modeling framework using large area simulations. So the black line basically is the TKE, the turbulence kinetic energy from the large area simulation. And the blue line is the PBL scheme. So basically near the surface, we can see the PBL almost have a factor of 2 greater TKE compared to the large area simulations. And we note that this issue is mostly because of the mismatched, the PBL and the surface layer parameterizations. So we just took a look at the KM in the PBL depths. So because hurricane modular is basically it's neutral conditions. So we assume the TKE budget, the TKE generation by vertical wind shear is balanced by TKE dissipation. And we can simply derive the KM formulation here. So the CM that's used in the AD viscosity basically is a coefficient, and the CD that's the coefficient using the TKE dissipation term. And they have some relationship I will dismantle later. And LK is a mixed length. For the convenience to derive the relationship between the CM and CD, we assume the mixed length and dissipation length scale is similar or the same value. And S denotes the shear. So at the surface layer, we can similarly derive the KM formulation, and we can compare the two formulation. We find to match the PBO with surface layer. So these two formulations need to be the same or equivalent. So that means the CM cubic will be equals to CD. So that's a very physical constraint to match the PBO and the surface parameterizations. And based on that, and original EDMF TK scheme uses CM and CD equals to 0.4. Yeah, so also one caveat is they use different length scale of mixed lengths and also the dissipation length scale. But I want to mention that if we use different length scale, it's very hard to derive relationship between the CM and CD. So we just go forward and we derive one value, especially the CD, that can be derived from the large unit simulation. We find its value is near 0.12. That's also similarly found in the previous mutual boundary from the earlier large unit simulation or even the observations. So, and then we derive the CM based on the relationship, that's the 0.555. And now the mismatch issue is addressed. And we also have a few, just mention that even though it's based on the neutral assumptions, but we can apply this relationship beyond the neutral condition because it have the morning optical similarity theory in the surface layer. So that can make this applicable to the stable and unstable conditions. And several other important upgrades. So first one is using a smaller asymptotic length scale. We can think that that's the turbulence, like a turbulence size above the surface layer. And we derive that information from the areas and also from the observations, from the DRINGS observations. And so that's using a value less than 100 meters. And that's suggested by both areas and observations. But we mentioned that that's only applicable for the moving nest. So for the parent domain or for the global nest, that won't be affected. And we also adopted the new PBO high definition. That's another important upgrade because the original one using the bulk Richardson number, that definition is not applicable for hurricane conditions pretty well because there's a dominant shear below the first model level. So imagine 10-meter wind about 40 or 50 meters per second, the surface wind will be 0. That's too extreme shear. To make this PBO height definition does not work. So we calculate the PBO height above that first model level based on the previous studies. And right now that performance is much improved. And another important upgrade will be the mass flux tapering in high wind conditions. That's to mimic the physical process, like the vertical wind shear in high wind conditions can dampen the rising plume in the convective boundary layer, but that's only applicable in high wind conditions as well. So with this upgrade, so right now the red line here is the modified EDMF TKE. So compared to the black line, the areas, both the TKE and also the AD viscosity matches better to the black line. That's areas results. And but right now we also want to mention that the improvement so far is mostly focused on the AD viscosity related mass fluxes. Because right now we are in the EDMF era, so we have AD viscosity diffusivity and also have the mass flux. So there are two mass flux components on the right-hand side. And then the second one will be the surface-driven mass fluxes. And the rightmost one will be like the downdraft because of stratocumulus top-driven. That's a radiative effect, basically. And it's typically very small in hurricane conditions. And so another task in forward will be to address how the performance of the mass fluxes in the hurricane conditions. I give an example about the axisymmetric structure of the mass fluxes, especially the surface-based mass fluxes. The shading is mean that. And the black line here means the tangential wind, azimuthal mean tangential wind. So that probably cannot be seen very clearly here. So when the shading is red or orange, so the surface wind is a hurricane force wind speed. And we also have the red line, that's the cloud base. The cloud base height is nearly 500 meters. But meanwhile, we noticed that for this mass fluxes can extend to 2 kilometers. That's very similar to the shallow cumulus steps. And I think the next step we were going forward is try to unify the mass fluxes, especially from the PBO, EDMF, and the shallow cumulus, because that's one key step to do. Because For the shallow cumulus boundary layers, there's convective plume developed in subcloud layer and subplume developed between the clouds. And we want to the mass fluxes can be just mimic this process continuously instead of just treat them separately in a PBL and shallow cumulus. Yeah, that's all I have today.
This is a part of physics that you're planning to put it for HAFS as well as HAFS.
It's yeah, right now it's mostly for HAFS.
HAFS,
Yeah,
basically.
yeah.
Zach, do you?
Yeah, Xiaomian. So yeah, nice presentation. And so you already presented the TC PBL schemes. And what is your plan? I mean, we have 2 months to fix the physics issues. What is your plan to further improve the HAFS configuration?
Yeah,
intensity forecast.
Yeah, there's one feature I didn't notice in the second page. So I just have like experimental design to address a little bit about the Dalva counting issue of mass fluxes. So it looks like it's a little bit more aggressive right now. So I will try to, yeah, there's some threshold to tune that. So like when we turn off the mass fluxes in the hurricane conditions, so we can do that very easily. Like after this conference, we can do that with Andy, and we have some plan to do that. Like, yeah, that will address the R34 issue as well. So I'm pretty sure about that.
All right, thanks.
Yeah.
Zach, can I put you on the spot? Sorry about that. Yeah. What is that you're envisioning? Like we see there is going to be a lot of physics experiments coming up other than DA. DA is going to be a section that's going to be talked all the time. And I see a lot of concerns because long-term, the intensity is of concern with HAFS. So do you have plans and what do you want the community here to do? What are the kind of experiments that you're envisioning so that we can be of help?
Okay, so there's 2 parts. So for the initial, right now we have a spin down, spin up issues, which probably related to DA system, or also the VI vortex initialization. So that's will be one. And the second one is long-term intensity forecast for the longer lead time. We have issues, we have larger, like relatively large degradations. So this, we think it could be related to the physics. And I think most likely I would expect currently we have several plans like to turn off the deep convection schemes. And we are planning to do that now. And also another area of we are looking for is the PBR schemes. So that's basically 2 of them. And I'll just think because Olivia asked me a question about the West Pacific different physics configurations. What I'm thinking is that right now the issue with the West Pacific, it has a large higher mountains, like Tibetan areas. Like we have some failures, so we have to use larger damping coefficients. That's one, at least for HFIP, we did that. And also we have to tune some model physics to avoid the failures. And also, I mean, there's different behaviors for the West Pacific intensity forecast. So we have to use different physics schemes. Yeah.
I mean, different tuning parameters. Yeah.
The same physics, same model physics, I would emphasize, but we have to tune the different coefficients.
All right, my name is Hyun-Soo Kim from AOML. I like it in your suggestion, bring up the lowest level PBL, bring it up to 20 meter, which is great. The current setting up is 10 meter, and then when wave comes in, wave usually go up to 15 meters under the hurricane season, under the hurricane conditions. Definitely violates all the assumptions so you made in the surface boundary layers too, and also I like it. You're talking about the shears in the boundary layer too. We have to consider ocean currents as well, right? Because in order to make it wind shear perfectly in the boundary layer as well. So that is one, a couple of my suggestions you have to consider too. And then, that ocean parts in a PBL or surface boundary layer has to be connected with the marine boundary layer, right?
Yes,
So,
yes.
we do working on, ocean coupling, but it doesn't seem to be, make a, impact. I don't see the ocean model impact on the boundary behavior. So it appears that we have to more, pay more attention to the surface boundary layer and to make it connect to the PBL as well as, ocean surface boundary layer as well. That's
Yeah,
my
yeah, totally agree.
Yep.
Thank you. And yes.
Because we only have about 2 months after, after the end of the season to fix all those problems. So we may need to prioritize our time and our effort. So this is very promising scheme. I would like we probably explore more. So you may think about your timeline to work on this, and the biggest concern still is the time constraint for us to freeze the code. So I like this this type of, I would say not tuning. This is not really tuning, but one big things you probably think about is how, because you are working on more oriented to hurricanes regime. So what about the regular, say, stone track regime? Have similar feature. So what do you want to do for this?
Yes, that's excellent comment. Like, so I just briefly mentioned the idea to unify the physics, especially the PBL mass flux, because we need to be aware of that. The mass flux idea is actually coming from the cumulus scheme. So when we introduce the idea to the PBL, why they cannot just do the similar job as shallow cumulus? So that's what I concern here, because right now the PBL mass fluxes, if it is moist sponge layer, it will be called, and shallow cumulus will be called second time. So that can cause the overmixing sometimes if there's if both of them are activated. And like, for example, if yesterday, I think that there's to have a talk like mentioning there's a sensitivity region, especially in the west of the subtropical ridge, right? Yeah, this shallow cumulus mixing can affect it about the strength of the ridge. So I think that's also related to the track. So that's something bearing in mind. So this is really beyond the intensity forecast. So unify the physics, that just gives some promise for the longer term, like the track forecast.
I can entertain. I'll go to Andy first and then come back to you. Andy, go ahead.
Yeah, the other thing I was going to mention that Shaman and I've talked about doing is, we've talked at the MC about this, is implementing the TCPBL changes into like the global model itself, like GFS, and doing a set of sensitivity tests, maybe like run a month with that versus like the default, and maybe even include Thompson, and just see how it affects the large, TC, you can look at TC tracks and things like that, but also just the large scale. And I think that would be pretty insightful and could also be applicable to HAFS across a variety of scales. So we're, obviously we have some other tests for HAFS we may have to prioritize, but that's something we're talking about doing in the next month or two.
Thanks, Andy.
Yes, I have a question about the physics. As we know, under the hurricane conditions, the dissipative heating is very important indeed for the strong storms. I don't know whether the current version included the dissipative heating or not. And because the boundary layer scheme now seems to give reduced the TKE by 50% in the low levels. Yeah. This is a large reduction of the dissipative heating if you included the dissipative heating in the model. Right. So that's my question, whether the model not currently, whether the dissipative heating is included or not.
I think I can answer it myself because I've seen the code myself. Yeah, it is included in the TKE scheme. The way the TKE is done, jungle scheme, it automatically includes dissipative heating. Yeah, but on the contrary, what we have found with HFIP on this dissipative heating, we try to actually evaluate the distributed thanks to Johnson's observations, we found that term to be very, very small. So in any case, I think with that, do you want to have any say on the physics, or we can move on? Yes, I think, yeah, what was not covered though is how long-term, convection is one of the main areas I would have expected that we need to probably work on until we have, because we work on a scale spanning convection scheme. Yeah, that's, first let's start with convection because we are talking about track degradation. So, yeah, so radiation comes next after convection, but maybe later on we can talk. I'll give one more, I'll put Curtis on the spot. And do you want to share your inputs because of CAM and what do you do with your physics schemes, basically? Do you want to have any comments? Because you don't have convection in the sense you only run it with microphysics, right? In the inner high resolution.
Yeah, thanks for asking. We are also struggling with mostly experiments and configurations running with 3 kilometer grid spacing. So we're right in that gray zone of whether you're not resolving the convective processes. So we aren't running with deep convective parameterization in the RFS configurations, but we are looking at the shallow convective part. That includes right now the treatment of those clouds on that process, those shallow Q processes and their effects in the MYNN PBL scheme. So that is a component of, I think, how we have to treat convection on a 3 kilometer grid. We've seen, I guess I'll leave it at differing impacts when you have the deep convection on at 3 kilometers. I think it can help in some metrics in terms of precipitation scores. It hurts in other metrics right now with things like reflectivity when we do verification against that. It tends to reduce the overall intensity of the convective features, can change their structure when you have the deep convective scheme on at 3 kilometers. So it's an active area of research. I think we can make progress there and have a more effective scale aware Q scheme operating at that scale. But it's definitely, depending on your metric right now, it's problematic to have that deployed. So shallow Q, yes, deep Q, no, for the work we're doing right at the moment.
Thanks, Curtis. It's a point well taken. And that's one of the direction, like trying without convection scheme. That's what in the inner nest, that's what Zach was also. That's one of the experiments that we might have to do within the next 10 weeks, probably. With that said, I think we can quickly move on to the DA part of it so that, yeah, Young Hoi, you can go ahead. Yeah, you can go ahead with your discussions on DA. I have that at the end because we are going to continue on a bigger session in the afternoon, which will be run by Avichel and Zujin, so that we can start from here on.
Okay, thanks everyone. So in this year, we just conducted HAFS A and HAFS S, these 2 systems in this year, and so the HAFS A and HAFS S both has the DA in that. So this year we just use the inner core data examination DA, and so the left top, so the observations for the data examinations, so we can notice except the radius and for the gray the MV, the satellite derived velocities. So except the MV and the radius, we have a very small number of the convection data examinations. So compared to the basin-based data examinations, the left bottom is the data estimated observation numbers from last years. So we can compare the observation numbers. So last year we estimated about 1.8 million observations for almost each cycle, and this year we just have 60,000 for each cycles. So for the middle panels, we just showed 1 cycle MV observations for the distributions. So the right panel, we just want to investigate the observations impact on the HAFS focuses. So we designed 3 experiments to compare the HAFS A systems. In the red panels, the cayenne colors is HAFS A, and the green is. So we just remove the dynamic observation errors, and for the blue, we just remove the HDLB winds, and for the purpose, we just remove the satellite winds. So from these experiments, we didn't tell any difference for the track forecasts, and for the intensity forecasts, within 48 hours, we can see when we remove satellite winds, we can get a smaller intensity of errors. So for this one, we still working on this to investigate the observation impacts, and also we plan to investigate the radiance observations to the HAFS focus next plan. So another DA impact investigations, we just do the VI and the DA experiments. So this year we implemented the VI to our DA. So we run the VI and then run the DA systems. So here we designed the code study in the blue lines at the top left. The blue line just start the HAFS focus from the GFS analysis and use this GFS focus as a boundary. And then we run another experiment for HAFS VI only, that's cayenne colors. And then we run the DA only experiments for the green, and the VIDA that is a HAFS real-time systems. So for the red colors. So for this experiments, we just run 2 storms for the Ian and the Fiano in this year. So for this experiments, the very simple result is we can see when we only do the DA experiments with 66 hours, and we can get a very small errors from the track and the intensity for the DA only. So this one we just may notice us that the DA may be not the issues for HAFS spin down issues. And for us experiments, we can notice after 66 hours, the code start and the VI only and the DA, VIDA has the same results from the track and intensity forecasts. So the right 2 panels, I just showed the 6-hour forecast from each cycles to compare the spin down or spin up issues. And I didn't get any result from these experiments, and just show you all these figures. So from here, we can just notice that for code starts, we have spin up issues. So that means we just from the start the forecast from global and from the cost resolutions, and they get the system stronger. And for the VI and the DA, and even for the VIDA, we don't have a experience the spin down issues here. So next slide, we just show the same experiments for the Hurricane Fiona. So that's my investigation. Thanks.
Yeah, we can entertain one question before we break. Anything related to DA question that anyone has? Any questions from remote participants? Quite welcome now, because we'll disperse for our break right away. Zach has a question.
No, I just have, actually, I don't have a question. I just have a comments on the slide 1. And Yonghui is showing the distribution of high resolution AMV data. Actually, this one is not included in our real-time experiment, but this is a high resolution AMV data, and if everything goes smooth, we are going to use this real-time the high resolution AMV data in the HAFS version 1.
This is a lot of the high resolution image. This is the regular.
Yes, the
image.
distribution showing here is not high resolution.
Yeah. Correct.
Yes.
All right, we're gonna have to stop for our break, but before we go into our coffee break here, I wanted to take a minute, if everybody in the room wouldn't mind coming up to the front. And Jenny, if you could put the people online's faces up, we want to get our group picture since we're going to lose a lot of people today because of the weather tomorrow. That way, at least we have some record of our good turnout in person and online. Don't be shy. Just, yeah, and just try to stay out of the main beam of the projector as much as you can, I guess. And those of you online, if you feel comfortable, it would be great if you could turn your cameras on so we can get a picture here.
Why is nobody sitting in the middle and not realize, oh, there's a bunch of faces in the middle? Jason, you're right in the middle. Yeah. Thanks. I sent you a chat. Oh, no, I'm not.
We should have stand on the table, otherwise you couldn't get it. Yeah.
You can lay down on the floor, Vijay.
Go over there so you don't fly the projector.
Oh,
Come on. Right there, go Paul.
kneel in front of Gina.
Feel that. All right. Make like you know each other, or whatever it is.
There's a lot of people. What do you want?
Yeah, I know. I'll take like 4.
Ooh, I broke the podium. Sorry, guys. So we'll be back at approximately 11 o'clock for the next session. For those of you online and in the room, if you are presenting after our break or after lunch and have not uploaded your slides, please do so as soon as possible, because we are short on quite a few sets of slides. Thank you. See you in about 12 minutes or whatever it is. All right, welcome back. The session that'll bring us from now through to the beginning of lunch at 12:30 is planning for 2023 real-time session. Session chair is Gopal. First talk is Shujin and Zach. And Avachal. You ready? Yeah. All right, take it away.
Thank you, everyone. So I need to get used to look at this distance to to read my slide. So I'm doing the most is the planning work for the work for next after IOC. So I think this is important, even though maybe the future plan will change all the time, but it's still very important. Next slide. Or can I move this? Okay. So this is what I was tasked to develop the app. Leader that Hurricane application team with Zach. So we have this cross-cutting team work with us to put into our app. So we need to touch every aspect. That's the hardest work. We need to interact with our teams. Okay, this is how complicated our system. I'm not going to explain you to each component, but this is how we put the system together. So in the left side, that's a high resolution deterministic coupled HAFS. Then the right side is the DA part. So you see so many components and they are moving quickly. So it's very hard to align everything, but we also need to prioritize our work according to the funding situation and the resource. But that's our ideal situation for the future work. So here is the current status of the workflow. It's already there. I just show you that so that the system can work in the real-time situation. And the moving nest, it's already put in place. That right now is a single stone following moving nest, and we have auto stone tracking system, so that the moving nest can automatically track in the model. The ocean part that is important component. So we developed this system. Currently, we only have two-way interact an ocean and an atmosphere, but we have only one way with WaveWatch. We watch 3 model. So in order to make everything work, so that the system build a lot of the utility for DA and VI. So these each component in that figure. I put a big block of DA part for the current system. Zach and Bing and the DA team they put together. So I'm not going to explain the detail. On the lower right corner, that's the system we're going to put together, and each domain for the IOC. So the biggest orange domain, that is the ocean domain. Then the dark blue part is the WaveWatch. Then the mnemonic domain and the red nest domain, that is atmospheric component. So here is the problem, because the issue drive our development priority. So we can see this. So look at this. At the initial time, we already have problem. So the biggest spin up, spin down issue, that's certainly related to DA and vortex initialization. So that's one of the things come up several times during the previous session. So that is our priority. One of our priority. We'll work on that. Afternoon we have a full session about DA requirement, and I wanted the community come up a solution for us. We will adapt to the system what you proposed, but what's our requirement for the system we will propose, and Avich are going to present that requirement in the afternoon. And meantime, the DA and the vortex initialization combined together, we're still having, why is it not moving? Which point I should? Click the screen. Okay. so I should put less animation, but the things I want to point out is day 4, 5 still have a lot of issue in the model. So that's already demonstrated by Zach and Bing and others showing the intensity issue. This doesn't work. Just your side probably. Okay, so this is my real things I want to show here. Moving nest, we want go into the global nest, a global moving nest and a multiple storm. That's one of the emphasis. So another thing is the telescopic moving nest for future IES capability. That is, we are planning to do that. And the DA part is really several things restrict us to move forward DA. One is the efficiency, how fast we get the more data and less time to get the initial condition. Another one is we are explore the AI machine learning technology for DA. This is already explored in other operational center like ECMWF. So like next week, they're gonna have a whole day discussion about the machine learning and AI technology for DA. So that's another thing. The ocean and the atmosphere coupled DA that is already have a lot of development in global model, and we probably also going to that direction to work on that. Another bigger thing is right now, community and the developer not mentioned too often, but it's really have bigger issue, the CRTM compared to the RRTMG. That is two different scheme. One CRTM is for data simulation, satellite radiance data simulation, but it's RRTMG that right now is in the model. So that is really the difference between these two things. Then when we do the DA, how can we calibrate the CRTM and the RTMG? And we have several JTTI projects work on the scale-aware DA technology and the particle filter DA technology. Those things will present in afternoon. So you will have a peek about what they are trying to do. But of course, mine is after IOC. So it's all the planning work. And NOAA is invest those money to develop the new scheme and the DA and the physics parameterization interaction. So actually during the break, Bob mentioned to me this like, physics and DA part, but especially the DA, how much the physics parameterization impact DA. That is another area we haven't emphasized enough. Observation certainly is the ideal situation if we have our observation for every storm. Reality is not. So how can we mitigate this type of deficiency in the observation side? So I think Joe Sion and other people, they start to explore those. We need a vertical profile. The one level data is not working very well. Certainly ocean part also. The products, that's our real contribution to the forecast community and the research community. If we don't have the product, whatever the model produce, no one knows that, then you still cannot get out from the advanced system. And physics, certainly, we will explore three areas. One is AI and the machine learning and the physics parameterization combined together. That's make the physics more efficient, may not exactly address the physics parameterization, but make the system faster That is one of the area we are explore. And then that is sub-kilometer physics. So we are prepared the future 5 years. We have sub-kilometer model. So what we're gonna do? The sub-kilometer physics right now, even though we have scale-aware physics, is those current physics scheme fit into the sub-kilometer physics? Parameterization is a sub-kilometer model, still question mark. So we will explore that. And then luckily we have one JTTI project is addressing one of the components as an exploration. So the another part is like physics need a talk. So Frank always tell me, hey, when you do the microphysics, they really talk with the radiation. That's just like one example. Physics need to talk. So this part we need to emphasize in the future. The ocean wave atmosphere coupling, that part is really still not explored enough. So this we need to in the future we need to explore, and I hope like we have more funding to support this area. So I think that's how can I do? Okay, so I want to say this. Operational is like we build the capacity for the whole bucket, but okay, in the reality, we have this type of the bucket, right? So the maximum capacity is depend on the shortest board. So for operation, we have everything needed aligned together so that you get the maximum capacity. Right now, we are in the development mode, some going faster, some going slow, but our current operational capacity decided by the shortest board. That's the things I want to emphasize. So that's why we have so many things, so many development going together. But this is the philosophical problem question we want to emphasize for operational model. Yes, you're doing your research, you just develop one of the board. If you can, go into up to the sky, that's fine. But in order to put into the operational model, everything need to come together. So we can reach all the capacity. So that's pretty much all I want to say. This is summary for your reading. So basically it's a three aspect. The moving nest capability is going to the multiple nest and the global moving nest and the telescopic nest. The DA part, we focus on the capacity build, then the new method and data ingestion. We have new data, the new data we're going to explore. The new physics, we want to make sure the new physics fit into the high resolution model. And certainly another thing is we are not alone. We are one of the application of UFS. So these have to, our development have to synchronize with UFS big community development. That's certainly we need to work with EPIC, work with UFS community to adapt their development pace. So it HAFS not alone, but we have some independence. That's all.
Thanks, Sujin. In the interest of time, probably we can entertain questions later on. Probably we'll move on to the next presentation, which is starting with moving nest anyway.
All right. Good morning, everybody. My name is Gus Alaka. I'm at AOML in the modeling group there, and I'm going to talk to you today about our plans for real time next year in the 2023 HREX, what we're calling the basin-centric HAFS or HAFS basin. And I put this presentation together with Bill Ramstrom, but obviously there were a whole array of collaborators at AOML and EMC who helped this work become possible. All right, next slide. All All right, brief table of content. So we'll go through the motivation where I'll touch on the basin scale HWRF for those who aren't familiar with it. Talk a little bit about some of our unofficial 2022 demo results using the HAFS version 0.3 basin. Talk about our plans for next season, and then a little bit more of a deeper dive into the plans for multiple nests. Next slide. All right, so basin scale HWRF, if you see me present anywhere, and especially at HFIP, I probably have talked about basin scale HWRF at some point. We called it HWRF-B, and it was our multi-storm application of HWRF. So you can see on the left side here, this is an animation of mean sea level pressure with just approximate nests. They're not actually drawn out in the way that they would show up in the model, but just to give you an idea of what storms are being followed by nests in this particular integration. And what we're showing here is in the solid nest, those are real ones that we were able to configure in that model, and then some hypothetical ones were ones that we missed, right? So in the future, we want to put together a system that maybe we can capture all of the tropical cyclones, you know, during a really active period. This was from the 2020 season when we had 6 or even 7 or 8 active tropical cyclones in the East Pacific and the North Atlantic basin. So this can be a common, I won't say common, but it can be a problem where you have a lot of active storms at the same time. And so, yes, you can run HWRF or HAFS multiple times in a storm-centric sense, but you lose some key things that happen in terms of the communication between these different tropical cyclones. So what's in the middle column here on the top, what we did is we ran a controlled experiment where we ran the basin scale HWRF, but we only ran it with one nest. So we ran it a lot like the operational HWRF, but nothing else was changed. The domain size, the DA, everything was identical except for the number of nests. The blue is the baseline for that single storm experiment, and the brownish red is what we got for our multi-storm experiment. So on the top, that's for the full sample. You can see that as we get beyond 60 hours, some notable improvements up to about 10%. Nothing that's off the charts, but some pretty good improvements over a large sample. And on the bottom, it shows when we actually stratify for situations when there were 5 or more storms, and we see those improvements go above 10%. And I encourage anyone who's interested in learning more about what we did with basin scale HWRF. Zujin, Gopal, and I have a paper that was published in BAM, so certainly take a look at that. We brought this all the way with help from EMC, obviously, to RL8, and we almost got it in as an operational version of HWRF, but we just couldn't get it over the hump. But I think that was a great example of the teamwork that it requires for these R2O transitions, and we're ready to employ the same type of approach here for HAFS. All right, next slide. So the 2022 HAFS basin configuration, we had a large fixed parent domain. So that was similar to basin scale HWRF. We chose 30 north, 57 west. And you can see as the center, and you can see that the thick black line, that is actually the edge of that parent domain. And we had a moving nest that could be placed anywhere in that domain. And a big thanks to EMC, especially Jung-hoon, who wrote the Python script that was able to find the right grid indices of where to place this grid. So another example of some good teamwork there. That's shown in red, the moving nest, and then the HICOM domain is shown there as well, but we did not change that here. We used HAFS physics and the vortex modification in HAFS as well. And the runtime was actually pretty similar because we degraded the resolution slightly to 7.2 and 2.4. I'll talk a little bit later about some of the downsides of that and our plans going forward in terms of the resolution and other things as well. All right, next slide. So some of the preliminary results, note here, very preliminary. We only had 64 forecasts that we were able to analyze here. We had a lot of technical issues that we were sorting through. And again, I look at this as sort of like a necessary part of the foundation so that we can build upon this configuration in the future. So we got 64 forecasts, and most of them ended up being early life cycle in storms. We were running a number of different storms, and we made it a certain way through the life cycle. So it ended up being a lot of weak storms here, and actually some storms that HAFS had problems with as well, which I'll touch on. So on the right here, we're showing absolute intensity errors, mean absolute intensity errors on the top, and the bias for intensity on the bottom right. And the mean absolute error was slightly worse. Our HAFS basin, sorry, the code name here is HF3B, is shown in the blue circle. So you can see slightly worse, but in the pack, and maybe a little bit more of a noticeable low bias compared, but pretty close to HAFS at most of those lead times, especially remember the sample was small. If you can go to the next slide, this was something that gave me some pause. So this is the track, absolute track errors, and there was some notable track degradation. You can see the blue line standing out on top. If you look at HAFS, this period and these storms, these cycles that we chose were problematic for HAFS in general. And Jamin and Andy touched on this a little bit. We ran a number of cycles for Henri, for example, which ended up being a storm we have to dig into a little bit more with this configuration to figure out how to maybe improve those particular forecasts. But we also think maybe here with the large static grid, the mnemonic grid is playing a role here as well, because we do have a variable resolution, whereas you get toward the edge of that domain, the resolution is not, it degrades a certain amount. So challenges going forward, we certainly had a lot of challenges trying to do the vortex initialization. So for that, it's hard coded to take a 45 by 45 degree domain, cut that out, and use that as your environment and separate the storm. But if your storm is too close to the edge of your parent domain, right, then your 45 by 45 degree domain falls outside. It's actually a fairly simple thing to fix going forward, but we just didn't have the time and the resources to do it right now. But one of the things we're considering, and actually I credit Bin Liu for coming up with this idea, is actually producing a separate VI grid for each domain. And so you actually have the 45 by 45 degrees that you need. You pull it right from GFS, and you have that for all of your applications. So we're actually working on a prototype for that now, but couldn't get that coded up for this meeting. And we had some module issues and other things that are run of the mill on these machines. So next slide, please. All right, here's some just quick results again. Good on the left, bad on the right. So for Fiona on the left, this was actually when it was Tropical Depression 7, or maybe even PTC 7 at this point. And the forecast was actually pretty good for HAFS basin here, the HF3B. It was sort of right in the pack with the other two versions of HAFS. And even though it was a little bit north of the best track, which is in black there, it did show impacts on Puerto Rico. So that was a pretty good, pretty reasonable forecast. And on the right side, this is from Henri. Again, touching back on some previous results, we saw some pretty bad forecasts, outliers in terms of track for Henri. And you can see that the HAFS basin is the one that's all the way out to the right, and actually had a 120-hour error of over 900 nautical miles in this particular case. So we have a little bit of work to do to figure out how much of this is the resolution, because it was worse than HAFS, and how much of it can we improve through some smart physics upgrades like Xiaomin and Andy talked about earlier. All right, next slide, please. So the prototype for next year that I'm envisioning, we have a couple of to-dos and a couple of options. So the to-do, I think we're going to upgrade the resolution to 6 and 2. That way we're consistent with what's running in the operational world. We're going to upgrade to the ESG grid. This is going to allow us to have more uniformity of our grid spacing all throughout this static domain. And to do is configure multiple nests as well. I'll touch on that in a couple of slides. An option, as I mentioned, is separate 45 by 45 degree domains for VI and DA. That way, if you have a storm like the one over in the East Pacific, and you're using this particular domain, imagine you try to cut out 45 by 45 degrees, right? This is what I was talking about earlier. You can't do it based on this domain, so you need some separate data. So we have some ways to get around that. I think we'll probably implement that, but some more testing will be required. And an option that I'm really excited about is cycling the parent domain, or at least getting an analysis domain that's consistent or bigger than the domain you're seeing here, and downscaling for the nests. And so Jason's going to talk a little bit about this, I think, later today. And we're really excited to collaborate with what's happening on the DA side. I think the initial vision is maybe having two separate workflows here, where one workflow is handling the DA cycling, and we'll actually pull from that analysis that's produced and initialize our domains, our moving nest domains. And computer resources are going to dictate which options are worth or possible to pursue next season. Next slide, please. So this is a little bit more detail on our ideas for phasing with the DA. So what we're going to do is essentially, like I said, leverage the cycled parent domain as initial conditions for this HAFS basin. And we could initialize the entire parent, or we could just initialize the nest. We have some testing to do to figure out how we can make that all work. But we're really excited to actually bring in some HAFS based covariances when we're doing the DA here. And like I said, separate workflows to get this done. So this figure was courtesy of Jason. I think he'll show something similar later. Here he's prototyping the more storm-centric HAFS, but you can imagine if you have your pink domain as cycling, and we set up our HAFS basin domain as being within that, or almost the same size, then the same type of application can apply to that HAFS basin as well. We're actually able to pull that analysis down from that cycled workflow. All right, next slide. So plans for multiple moving nests, and I credit Bill Ramstrom. He's doing a lot of the heavy lifting here. So, big thanks to him for all the hard work he's doing here. So going forward, he's going to be leveraging the architecture essentially put in place by GFDL to enable the multiple moving nests. And first step is going to be getting this to work on the parent grid or tile 7. So more in our regional version of HAFS. And so that's exactly the type of development that we're going to try to use right here in this HAFS basin, because we're going to have, a parent domain, a regional version of HAFS. But going forward, it's really exciting because it applies to the global configuration as well, where we can configure multiple nests on one or more of the cube tiles. So here in this image that Bill shared with me, you can see there's a moving nest on 2 different tiles where you have a storm in the Atlantic and a storm in the East Pacific. So this would certainly enable us to get a little bit, outside of our regional configuration and start to think of things more on a global scale, which I think is certainly exciting for the future of HAFS. Maybe not version 2, obviously, but as we go forward, certainly an exciting development that opens up a lot of possibilities. Next slide. And this slide was showed, or this animation has been showed already. I love showing it. I think Bill produced this one as well. This is the prototype for the future vision of HAFS, where again, you are able to put these multiple moving nests, you can place them anywhere in the world. So you have a tropical cyclone in the West Pacific and the Atlantic. It'd be certainly an exciting prospect to simulate both of those tropical cyclones at high resolution and understand how they interact maybe through the jet stream and other things like that. So with that, I'll take any questions or comments. Thanks.
I think we can have a couple of questions. One, you can also, because Sujin, you can direct questions to Sujin too, because it's a common.
Sure.
So again, I'm putting Curtis on the spot. How do these plans that Zujin and Gus talked about overlap with any of your strategies in terms of grids, resolutions, moving nests? What are your thoughts? I know you haven't even implemented CAM yet, but.
Sure, great question. So to start off with, for the Rufus RFS, we're going to have a large singular domain at 3 kilometers that's not quite basin scale, but it's close. The plan is to have a fire weather nest run inside of that configuration to reproduce the NAM fire weather nest capability that existed. So we will have that. It's not going to be moving to start with, but it will be a relocatable capability. The details of that, we're still fine tuning some of those specifics of whether it'll launch from fixed, hourly boundary conditions or literally be connected inside the model time step by time step for the nest. It may be the former rather than the latter at this point, but that's something we're looking at. I think a little further down the road, we're going to want to have a connectivity to the Warn on Forecast system, which is another on-demand nested system that probably dictates something like needing to have multiple at the same time, maybe moving. So I think then the parallels become even more applicable to HAFS. So I think we're going to have more conversations about what that looks like and some of the technical details there. So I think in general, we have some challenges that we'll need to overcome with the DA, in particular with the moving nest for the convective features that are going to be coming in and out of the target domain. So I think we have a lot more conversation to have when we get to that point. Again, that's certainly not in the initial operating capability for Rufus V1. So that's an overview, I guess I would.
Thanks, Frank. Thanks for initiating those discussions. We'll move on to GFDL updates of SHIELD.
Hi, everyone. I'm Tim Marchuk, GFDL. I'm going to be talking about real-time runs from a couple of the models that our FE3 group develops, shield and T-shield. These are actually just two different configurations of the same model, and I'll talk about that in a minute. What's shown here on the left is from one of our T-shield runs. It's a loop of maximum surface wind swath for a forecast that was issued 114 hours before landfall. And so it shows a very nice track forecast, makes that right turn just before Fort Myers. And actually looking at some of the colors, shows the rapid intensification just before landfall. Before I continue, I want to make sure I recognize the other members of our group who actually do the development of these models: Lucas Harris, Kun Gao, Linjiang Zhou, Jianwei Chen, and of course Matt Marin, who tirelessly make sure that all of these runs actually get run. Yeah, this isn't working. Okay, so looking at the two configurations, shield is on the left, T-shield is on the right. Shield is a global model, 13-kilometer resolution on the right. T-shield, also a global model, 13-kilometer resolution, but for the tile that's over the Atlantic Ocean, it has nested within a 3-kilometer two-way nest. Both models use GFDL microphysics that are in line with the DICOR. Shield uses an updated version, version 3 of the microphysics. T-shield still uses version 2. For convection, Shield uses scale-aware SAS. For shallow and deep convection, T-shield also uses that globally, except in the two-way nest. The deep convection is turned off in that inner nest, but the shallow convection still remains. Both use TKE EDMF, and both use a simple 1D mixed layer ocean. And importantly, both of these run from the GFS initial condition. There's no additional VI or DA that is done when we start the model. Next slide. So I'm going to talk about track and intensity and storm size. And I'll start off with track here and just go over a couple examples. Shield is on the left and T-shield is on the right for Hurricane Earl. These are life cycle track plots. And both models show a fairly good evolution of the storm tracks. T-shield had a little bit of spread in the cross track direction for Earl. Next slide. Forecasts for Fiona also were very good, close to the best track. And next slide. Hurricane Ian, there's been a lot of talk yesterday and today of the left bias that was evident in a lot of different models. And fortunately, for Shield, that left bias was minimized greatly, and in T-shield was almost non-existent. And that extends all the way back to the beginning at formation for Ian. Next slide. And I show that here for cross-track verifications. On the left are global models, on the right are regional models. And in both cases, our Shield models are in red. On the left, Shield is in red. On the right, T-shield for the regional models is also in red. And so on the left, Shield has only a weak left bias that's considerably less than that of the GFS and the GEFS mean. It's comparable to that of UKMet and ECMWF. On the right, T-shield has the smallest cross-track bias for Ian for all of the models included, and significantly less than the operational models. The one that's close to it is COAMPS TC. It's interesting that both of those models do not have deep convection in that inner nest area where Ian is. Next slide. So this is something that Kun Gao has started to look at, possible reasons for these differences in the track for Ian. And first thing he looked at, of course, is steering flow. And so he was looking here at 500 millibar geopotential heights and differences. On the top left is the GFS, top right is Shield, and the bottom right is the contours from both are overlaid, and also differences shown in the shading. And so from the contours overlaid in that bottom right, the 500 millibar patterns are very similar between the two. There's really not very much difference in the steering flow that's evident at least at 500 millibars. One thing that is evident is just visually a difference in the size in the storm, right at the center of the storm between the GFS and SHIELD. Here at 500 millibars, that also shows up in the R34 forecast for Ian. Those are not shown here. And so I know there was a lot of talk yesterday about, is it the physics? Is it storm size? Frank, you were talking today about initialization. It could be all three of those impacting this. So there's a lot more work to be done on this. Next slide, please. Okay, this is track verifications for the entire Atlantic season up through a few days ago. And again, global models on the left, regional models on the right. And for the global models on the left, the SHIELD in red has lower errors than the GFS, starting at about 24 hours. And that spread between the two continues to 5 days, where SHIELD has the lowest errors among all of the global models. And for the regional models, T-SHIELD had smaller errors than HWRF, starting at, again, at about 24 hours, and also had smaller errors than HMON and both HAFS models at days 4 and 5. So impressive errors throughout the season for it, for track. And the only operational model that beat it was COAM's TC, the CTCX version. Next slide, please. And so one slide here to show track verifications from other basins. And this is just the global models, obviously. For the Western Pacific on the left, SHIELD was better than the GEF's mean at days 3 to 5, and it was marginally better than the GFS, although that's not statistically significant. And on the right, in the Eastern Pacific, SHIELD had nearly identical performance to both the GFS and the GEF's mean. They're all piled right on top of each other on that plot. But none were close to ECMWF there, which had incredibly small errors for this sample of storms in the East Pac. Next slide, please. For intensity verifications, T-SHIELD showed larger intensity errors than all of the other regional models. And here I'm just showing regional models, errors are on the left, biases on the right. We believe this is due to the fact that the model starts with a vortex that's initialized in the GFS. We have no vortex initialization, and was unable to catch up at later times. By the way, this is late guidance, not early guidance. For the biases on the right, SHIELD had a stronger negative bias, again, due to that lack of vortex initialization. It's similar to most of the other models in its negative intensity bias trend at later lead times. Next slide, please. Okay, size verifications. This is for regional models, just in the Atlantic. Errors on the left, biases on the right. T-SHIELD in red here is about in the middle of the pack for our R34 errors on the left. But it did have somewhat of more of a negative size bias initially than some of the other models on the right. And interestingly, all of these regional models show a tendency towards a more negative size bias with the increasing lead time. And next slide. And for global models, due to sample size issues, I only compare GFS and SHIELD here. And SHIELD has larger R34 errors, and also a negative R34 bias that increases with time relative to the GFS. Next slide, please. Continuing work this year, I want to investigate the skill of T-SHIELD for TC Genesis. We have an opportunity here. Our T-SHIELD forecasts go out to 7 days. And so we have an opportunity to see with a pretty reliably available set of high resolution forecasts, how such high resolution forecasts can do for TC genesis. And then also continue more with sensitivity tests related to Ian's track. And future plans, implementing the latest version of GFDL microphysics into T-Shield, refining the shallow convection scheme that's in T-Shield, and also adopting the HAFS vortex initialization into our static T-Shield nested domain. That'll allow us to do some more work with looking at structure and intensity issues. And that's it. I'd be happy to take any questions.
Thanks, Tim. Any questions? Yeah, Andy.
Hey, Tim, nice talk. Quick question on those R34 verifications. Did you run your updated tracker on HRF and HMON or just use what was in operations?
I just used what was in operations.
Okay, because I someone could correct me if I'm wrong, but I think they may be using the old version and that's slightly different from HAFS. So it'd be interesting to see like what they would look like with a uniform, you know, because like I noticed HMON had similar issues to what HAFS has had, but maybe that's a function of the different trackers. So I don't know.
Yeah, and I think there was something wrong with the HMON data. It might have been a post-processing thing because its R34 errors were not realistic, not consistent with how well it does with intensity.
Right. And so, yeah, it seemed like something was odd with that. So.
Yeah.
There's one more question.
Hey, Tim, big shout out for your newly developed the tracker. So I will try to test the results. So meanwhile, I noticed you shut down the basket deep cumulus for the T-Shield. So I just wonder, like, what's the impact of the T-Shield to the track and intensity performance if it's turned on in the current, based on the current configuration?
So you're asking what impact does it have to turn off the deep convection and just leave the shallow on?
Yeah, basically because right now the looks like there's some initial errors definitely, but just wonder how that impact the intensity forecast as well as the track forecast of the high profile, for example, the Ian. Yeah.
So I can't give you I'm not the one who developed that. If there's anyone on the line from GFDL who would like to respond to Xiaomin's question. But yeah, I'm not familiar with the details of that.
Yeah, can you hear me? This is more standard.
Yeah.
I think you made a very good point about the impact of the deep convection, turning it on and whether that will impact the track. I think that's something we really ought to see. I suspect it may have a lot to do with the differences in the bias. But that's something which I think we really ought to see.
Yeah, I think I have one more question. Probably we can postpone the question later on. So
can I say something, Gabo?
Yeah, go ahead, Jai.
Oh, okay.
Go ahead.
So I just saw the T-Shield or even for shield predicted a smaller and weaker storm. So this means the deep convection may help strengthen the storm, remove some of the bias for intensity. So for the track like for Yan, so maybe we already talk about the storm size or storm structure in vertical. So will play a bigger role for the left track bias. So that's why I just guess the should have a better track. So the deep convection plays a big role here.
Yeah, that's a good point, Jai.
Okay, yeah, quick question. The bias in the R34 for observational studies show that storms can grow in two ways. One is you get convective heating outside of the radius of maximum wind and it's forced by the convection, or you interact with baroclinic zones. So I was wondering if there's a deficiency in the physics where you're not getting enough convection outside of that inner core that's causing the low bias in the radii. It's something you could look at.
Oh, it's interesting. Yeah, and something that would impact it. How would that impact it towards the later end of the forecast? Because it appears to be a decrease with time. Yeah, that's interesting. Yeah, yeah.
Probably we'll move on to the next question.
Yeah, Tim, this I just make sure I understand the your configuration, the shallow convection and deep convection. You really switch off the deep convection and keep the shallow convection there, right?
Yes, all
I
within
just-
the scaleware SAS scheme.
Yeah.
Turn off deep and keep
No,
the shallow.
you depend on scale well, or you physically switch off the deep convection.
It's, as I understand it, it's turned off.
Okay.
Yeah.
Yeah. No, I just make sure that I understand your configuration, then draw the right conclusion. Because right now, in our system, we're not able to cleanly switch off the deep convection.
Oh, interesting. Okay.
But just bear in mind, we do retain the shallow convection, but we've retuned the shallow convection in a way that we think is a much more reasonable approach. So we can talk about it offline.
I think we'll talk about this offline. The next one is GSL update. Olson is, he's the one who's going to.
Do you mind if I share my screen?
Yeah, go ahead. Thank you. We're able to see it.
Hold on a second. Okay. Okay, can you see it now?
Yes.
Okay. Then. Okay. Okay, yeah, so I'll be talking about our contributions here. I want to call out special thanks to Hannah Barnes and Hai Chin Lee for their work. They put together probably over half of the slides I'm going to present. The goal here was really to test some alternative physical parameterizations within a GFS prototype during this past hurricane season. So we proposed to run two different experiments. One, simply replacing the GFL PBL scheme, or I'm sorry, the GFS PBL scheme with the MYNN EDMF scheme, which is currently used in the RAP and HER and slated for use in RRFS. And another run that replaces the SAS convection scheme with a new aerosol-aware version of the Grell-Freitas convection scheme. So we did a version of this. I'll explain some deviations from that on the next slide. But I'll present a wide variety of some tropical cyclone verification as well as some general NWP scores at the end. So yeah, the initial plans were to run these experimental 7-day forecasts, each day initialized at 0 UTC based on the prototype physics. But when we first started running our schemes just plugged in as is, we noticed we definitely needed to do some calibration configuration to make this a worthwhile effort. So the table here shows that basically there's in green, those are the departures from the GFS version 17 prototype in each column here. So what we propose to do is just switch out these schemes. But actually in both of these, we actually went with the MYNN EDMF because we have better overall radiation balance scores. So there's going to be a GFS GFMYNN and a GFS MYNN. As you can see from these other columns here, there's been additional tampering. So let me explain. This is really just a radiation interstitial scheme that we use, right? It's called right before the RTMG. It just allows the subroot scale clouds that are predicted by the MYNN and the GF scheme to be seen by the radiation scheme. That's all we're doing here. There's also a known low bias in soil albedo and NOAA MP, and it's pretty significant actually, especially over arid regions where that low soil albedo is going to matter. It's so large actually that it can impact your zonal means by 4 to 5 watts per meter squared even. So that's just a little little hack to brighten up the soils a little bit. It's a small impact overall. You can see there's one other column over here where the GFS prototype uses the non-aerosol aware version of the Thompson microphysics scheme. And we chose to use the aerosol aware version, which is the same thing we run in the RAP and HER and are using for the RRFS as well. However, it does have some high precip biases when you run it at long time steps. So basically the rest of the time steps, rest of the physics is time stepped at 150 seconds, but we had to sub time step this like twice per time step. So it only runs at 75-second time steps, basically. After all that, we thought we were in the ballpark with reasonable configurations. We did some preliminary testing. And here, this is all focused on running in the global framework, running at C76 resolution, and always initializing off the GFS for initial conditions. So our initial cases, we took a handful of cases from the 2019 hurricane season. And I'm only going to show you results from a couple of them here. One single reforecast per hurricane. We didn't do a set of them for each event. So here's just one example. Hurricane Lorenzo 2019 is a very strong Category 5 hurricane. You can see from a bird's eye view of the track that none of them did that poorly overall, but from looking at the position area, you can see that the MYNN version of the GFS did significantly better, especially at later times relative to both operational versions of the GFS and the version 17 prototype. However, none of them really captured the full deepening of this event. That all went down to sub 940 hectopascals. The MYNN did do the best overall, but still, they did not. None of them captured that rapid deepening. Moving on to Humberto, this was another large hurricane that impacted Bermuda. As you can see, again, from the bird's eye view, none of them departed that much from the best track. In this case, the GFS prototype actually did pretty good, but the experimental runs hung with it pretty good, and all of them outperformed the operational GFS. And for this case, they had rapid deepening down to about 950 hectopascals, and the MYNN did the best overall here, with P8 coming in second. So moving on to the last season, I'm just going to focus on Hurricane Ian here, and the well-noted left of track errors here were just at best minor, slightly reduced, and these experiment runs that really weren't taken care of, put it that way. Overall, if the next slide, I'll look at this a little bit more cleanly. But first on the top, let's look at some variations for a lot of different cycles here for the wind speed. And you can see that there were some runs that well captured the strengthening overall, but the lion's share of them were a little bit weak overall. And this is pretty much the same for all our experimental runs too. Overall, the total track error was a little bit better predicted by the GF MYNN. And with the GF MYNN, just the GFS MYNN coming in second overall. When you look at the cross track error, the MYNN typically performs better than the other two, but the along track error tells a different story. Usually the GF MYNN was the best between these three global configurations. So moving on to some bulk stats for this past hurricane season. Here I'm looking at the total track errors here for the Atlantic Basin on the left and the East Pac on the right. You can see overall that the MYNN version had the smallest track errors for most forecasts, especially later on. In the East Pac, both experimental runs kind of separated from the operational GFS, by, let's say, day 4, and the MYNN looking the best even out to day 6. Going on to a long track errors, this tells a little bit different story. In general, for the Atlantic hurricanes, the GF MYNN performed the best out through day 5, and then the GFS actually did the best between these schemes after day 5. But in the East Pac hurricanes, it looks like they're all pretty similar overall. Only later on, like around day 6, day 7, that's when the experimental runs pulled away from the operational GFS. For maximum wind speeds, you can see they're all, for the Atlantic basin, they're all under predicting the overall. And these aren't stratified by, weak hurricanes or large hurricanes. This is all of them during this entire period. The GFS, operational GFS actually did slightly better than the experimental runs. Again, we did no tuning for this specific metric at all. We're waiting for the season to end to get good stats to make that move. The East Pac looks like the GFS actually had a slight high bias, where the experimental runs were more neutral or even negative. Moving on to some bulk meteorological stats, here's the 500 millibar anomaly correlations, the raw correlations on top, differences from the GFS on the bottom for global and northern hemisphere and southern hemisphere. You can see that overall the experimental versions did result in some improvements overall, and that's mostly seen from the benefits in the southern hemisphere, where it even became a little bit statistically significant around day 5. If we move on to the RAOB verification, this is for the day 5 forecasts against all RAOBs across the entire globe versus CONUS here on the right, RMSE on top, bias on the bottom. In general, for global, it looks like the temperature RMSEs throughout most of the troposphere were better in the experimental versions relative to the operational GFS. But the operational GFS did a little bit better for bias globally. And then it's a little bit more of a wash for if you just focus over the CONUS. Kind of depends on which height you look at, but the GFS operational did pretty good overall. For 5-day wind speed errors, again, this is a little bit depending on which height you look at. It'll depend on which one does the best, but overall, it looks like for bias, the experimental versions did at least as good as the operational GFS. But over CONUS, looks like the big winner was the GF MYNN, which had not only the smallest RMSEs throughout most of the depth of the atmosphere, but also the lowest biases. And if we just want to focus on the tropics alone, looking at the temperature biases, this is where the GFS actually performed pretty well overall. But from a mean absolute error perspective, the MYNN version of the GFS hung right there with it throughout most of the depth of the atmosphere. Moving on to wind speed and the tropics, you can see that in general, both of the experimental versions did pretty good relative to the operational version, below 500 millibars, even above. With the the MYNN version of the GFS performing slightly better for mean absolute errors. And then finally, I want to touch on some radiation. Now, this is where really I wish we had a little bit more time to do some tuning, because there's probably some low-hanging fruit here that can be done here to improve things. But I think overall, what you can see here is that there's some compensating errors up here, but the MYNN generally has a little bit less clouds overall, so it has more of a lopsided high bias and outgoing long wave radiation, whereas the GF scheme is probably the best. GF MYNN scheme is probably the best in the tropics, and the GFS does probably the best at the high latitudes. And it's somewhat similar for downward shortwave at the surface. I think both the experimental runs tend to do slightly better in the tropics, whereas the GFS did a little bit better at high latitudes. So in summary, I'd say overall these results look pretty promising. I think the GFS MYNN runs had a slight edge overall on the tropical cyclone verification with the lowest overall track errors. But for the bulk meteorological scores, such as the anomaly correlation and the wind speeds, the GSL runs definitely look better, but temperature biases and mean absolute errors were more mixed. Radiation balances, again, they're very sensitive to these changes, and especially just swapping out different versions of the Thomson microphysics scheme, if you go between the aerosol aware version or the non-aerosol aware version, requires significant tuning. But I think overall, we can say that the experimental versions did a little bit better in the tropics, whereas the GFS did a little bit better at high latitudes. So given these generally positive results, I think that, it really justifies some further development and tuning with these schemes within GFS prototypes. And specifically, now that we've accumulated a lot of results, we can really target that some hurricane specific tuning, especially the intensity bias. And of course, we plan to use this data set to look into detail and the aerosol impacts for Thompson and GF and how that impacts a wide variety of meteorological regimes in the future. So that's all I have for this talk. I can take any questions. Anyone there? Oh, no.
We can hear you, Joe.
Okay.
Not sure what's happening in the room.
Okay. At least someone heard me. I was worried for a second. But I have a feeling they can't hear me in the room.
It might just be they haven't turned on the mic yet.
Is that a problem here? Oh, okay. Joe, can you release your screen?
Yes.
Okay. And Javin Bao, PSL.
Yes, I'm online.
Go ahead. Yeah, probably you didn't hear me earlier. Sorry.
Oh, sorry.
There was a problem at my end. My bad.
No issues.
Thanks, Javin. Go ahead.
Okay. Thanks, everyone. Greetings. This is a talk about PSL contribution in terms of activities related to the UFS physics development. Next slide, please. So back in 2015, I led a small HFIP physics working group to come up with this wishful list. Then we wanted to mobilize and gain coordination to work on all the physics, particularly emphasize on the scale awareness. So the aspects we provided actually touch from all the components from cloud schemes, to cloud radiation interaction, to subgrid turbulence mixing, Ayer's interaction, to stochastic physics and observational evaluation. Next slide, please. Since then, thanks to this support from NGGPS program and US Hurricane Supplemental and the UFS RTO projects, PSL are able to closely working with the UFS community to improve and further develop all these components within the framework UFS. Next slide, please. In the interest of time, I'll only use 3 examples to highlight PSL contribution in this regard. Number 1 is a generalized process level stochastic physics. Number 2 is the process level assessment of 2 EDMF PBL schemes available in the UFS. And last but not least, a dynamically coherent 3D subgrid mixing scheme for the UFS applications at gray zone grid sizes. Next slide, please. So our stochastic physics is based on well-established physics. That is the Moritz-Zwanzig formalism, in which if you cast model equation in semi-group notation and decompose model state as grid resolved and the subgrid with the age of the Louisville operator defined here, and it can be found in details in the reference here, we come up with so-called the generalized Langevin equation, which we use as physical basis for our ongoing development of process level physics, stochastic physics scheme. This scheme has 3 important aspects. One is the resolved dynamics, which is the model itself. The third term is the noise or perturbation, which samples the PDF distribution of subgrade motion. What's most important is the interaction of subgrade and the grid resolve scale, which is expressed here as memory term, because it is integration of quantities that are dependent on the model state of at early times. So the take-home message is that you need to construct a very good memory term to make any stochastic physics scheme at the process level to work. Next slide, please. In the physics literature, stochastic process is described by the above generalized Lagrange equation are called multidimensional Lagrange processes. So generally, we can come up with two approaches to deal with the memory term. One is called autoaggressive moving average model. The other is just a general autocorrelation model. So in our simple first minimal implementation of this scheme, we have this stochastic Lagrange processes that is closely tied with any physical processes you deem necessary, you want to describe in a stochastic physics. So you can see that this expression is an analog with the generally used currently in our operational stochastic physics called random pattern generator. The only difference here in physics is that our pattern generation is based on physics, the information from parameterization schemes, while the currently widely used stochastic random pattern generators are just a stochastic state, does not have any information from physics. However, the pattern has been widely used for the current schemes such as SPPT. Next slide, please. I think I forgot to say to go to this one. I already mentioned this one. So next slide, please. So we implemented the scheme to the UFS GFS. This is a sample of the perturbation of temperature and moisture from a convection scheme. So you can see it's very, very connected with the process of the parameterized process, convection processes. So if we use this method, next slide, please, for just comparing with SPPT, because that's very fair and close comparison for 850 millibar temperature root mean square error in solid lines and spread in dashed lines. And the red lines are the MLP method we use for the replacement for the SPPT. And the green lines is the SPPT, and the black is the just initial perturbation only. You can see that with our method, the spread is significantly improved, particularly over the tropics. Next slide, please. Now I move on to our examination at process level of two parameterization schemes in the UFS. One is the hybrid EDMF scheme used in the GFS V15, and the other is TK EDMF scheme used in GFS V16. For the diagnostic study, the single column model is solely based on the UFS physics. If everybody understands what I'm talking about, CCP, if not, we can talk about this offline. Surface fluxes are prescribed based on the case, a standard case we've been using to calibrate our convection and our boundary layer schemes. Next slide, please. Now, this is a tendency from two schemes, output from the two schemes. On the top panel is the hybrid, top panels are hybrid EDMF, and the lower panels is TK EDMF. You can see that the tendencies are for temperature and specific humidity from the TK EDMF have physical flop in sign near the PBL top. And you can see that for the hybrid scheme, you do not see that. This we call the very unphysical feature of the scheme. Now, if you look at the next slide, in terms of cloud water in and out from the boundary layer scheme, left column is the V15 scheme. You can see that the behavior boundary layer scheme on cloud water is very physical. Basically, it's smooth and smear, the positive definite quantity. You look at the red column here, that V16, in our input is positive definite, but output can see there is a significant amount of negative cloud water. So this is very unphysical. So further results of sensitivity experiments show that this is due to the adjustment of thermodynamic quantities in the upward mass flux in this particular scheme, pinpointing the sources of the problem. Next slide, please. So in summary, our sensitivity experiments using the single column model show that the TKE EDMF scheme used in the GFS V16 mixes more strongly than the hybrid EDMF scheme for this particular case and for other cases too, particularly in the tropics. In particular, the non-local mixing is more dominant in the TKE scheme than the hybrid scheme. This unphysical realization of cloud water, as I mentioned here, is due to mass flux mixing in this TKE EDMF scheme, which is the root cause for the unphysical structure that I pointed out. We actually have a solution to eliminate this problem. We also wanted to point it out in our examination at the process level. We found that the two schemes has evolved an assumption that is not does not exist in other schemes, such as MYNM. This assumption basically is assume that the external function, that is a ratio of temperature over theta potential temperature, is constant with height. So in order for future unification, we strongly recommend we need to do away with this assumption. So last but not least, jointly we are working with the Florida International University, UML, EMC, work to develop a scale adaptive 3D TKE mixing schemes in the HAFS. The purpose of this project is to have a scheme that can treat subgrid mixing in a coherent three-dimensional fashion by relaxing the conventional assumptions of scale and formulation separation between horizontal and vertical subgrid mixing for gray zone grid sizes. Our approach is to blend vertical diffusion from LES experiment and the PBL parameterizations in the 3D dimensional TKE equations that we can adapt from WRF. The objective and deliverable is a scheme that is capable of mixing everything on subgrid scale in a coherent 3D-dimensional fashion. That's all for my update. Thanks.
Thanks, Jevin. One question. Any questions remote? Yeah. John has one.
I did not hear, or did not see.
Hey, Jevin, this is Jun Zhang from HRD. Nice talk.
Hi.
I have a question. So it's nice to show that you show the difference in terms of the mass flux of water vapor between the two schemes. So what my question is, what exactly caused that difference? Is that the parameterization of mass flux, or is the PBL turbulent mixing part? So which part caused that difference?
That difference between V16 and V15, you're talking about a hybrid versus TKE DMF. That is about a moisture adjustment process in the mass flux, which exists in V16, TKE DMF, but not in hybrid EDMF.
Thanks, Jevin. We move on to the next talk by Insuk on coupling. That's one aspect which has been missing. Now she can talk.
Thank you, Gopal. And thank you to my collaborators listed in here. Especially, I give a special thank to Dan Rosen, who was involved in very beginning about the coupling, building CMAPs, modifying NUAPC and ESMF. So thank you. And then for the rest of us, we're just tuning all the parameters and then evaluating coupling simulations. Next slide. Okay, so what this one shows, the HAFS subcomponent and the submodules. That includes the IOC configuration with the FOB3 and the HICOM in the red box. That will be HAFS version 1 or IOC. And then later on, we're going to work on the HAFS version 3, working toward the three-way coupling, which is shown in dashed black red lines. So all this effort is mainly improving LC interaction processes in the couple simulations. Next slide. Okay, outline of my talk is following current coupling status. We heard about all the bug in ocean coupling. I touched upon it, and then we do have a plan to extend the northern boundary for North Atlantic for new ESC grid or Gus's HAFS basin modeling, so that we can have a better overlapping domain with the atmospheric side and ocean as well. And the second one is validation for the 2020 TCs, and then especially focused on Danielle or 5L, followed by ocean verification. And then fourth item is lessons learned that I worked on three-way coupling based on HWAP HICOM waiver 3. So this one is a suggestion from the lesson that I learned for future HAFS version 3. And finally, summary and then future plans. Okay, so this map shows that HICOM regional domain in a different color boxes. Blue box is NHC basin that covers Atlantic and also Eastern and Central Pacific altogether. And red box is the Western Pacific as well as Northern Indian Ocean, which is a part of JTWC basins. And also finally the green box, which is covering Southern Hemisphere. So all three domains providing all hurricanes in the Atlantic side, typhoons in the Western Pacific, cyclones, Indian and the Southern Hemispheres around the globe. Okay, superimposed in the shaded box are representing the atmospheric model domain, which is a regional, with the moving nest in a square. So Atlantic Basin domain, it serves the ocean components for at North Atlantic as well as the Central and the Eastern Pacific. So next slide. Oh, by the way, so initial and then boundary conditions are coming from, one slide back, coming from the, actually initial conditions coming from global RTOPS, which is based on HICOM, and then that is solving 3D primitive equations with the KPP mixing. And the resolution is 1/12 in horizontal and the 41 hybrid in a vertical. Next. Okay, so this is schematic diagram of the set of the feedback variables through the CMAPs between atmospheric FOB3 and then HICOM side. So there are 8 variables coming from FOB3 into the CMAPs, and the CMAPs do all the interpolation and the weighting, and then pass down to HICOM. And then HICOM also sends the SSD to that most CMAPs, and finally goes into FOB3 through the interpolation. Next slide. So this is the future schematic model components and the two-way interactions. Additional MOM6 for ocean component and also WaveWatch 3 there. So this is again all the three-way coupling configurations. Further CMAPs is going to be evolved to take care of a three-way coupling. Next. So, I heard about the ocean bug, ocean ink bug, and especially it's coming from the wind stress. the sign is reversed. So this one shows that in the old, with the bug in a cyan and then bug fixed in an orange line for mean absolute error on the left column for track top and the V maximum intensity in the bottom, and the right middle panels shows the skills for track top and the V intensity, V maximum intensity in the bottom. So when you see this comparison between cyan and then orange line, yeah, definitely there is improvement in both, especially in the intensity side. However, the intensity maximum mean absolute error at the longer lead time that deviate, compared to HWAP, there's a large error exists, which is a significant, statistically significant. That is reflected on the V maximum biases in the skill area as well. So if we going into the bug fix that, I don't want to be a party spoiler, but you will expect worse intensity bias, especially going toward the negative. So I'll give you a warning ahead. Okay, next. So this is one example, Danielle, HAFS A, as well as HAFS S shows that very high intensity biases here. And the first thing you'll notice that the track predictions with the bug fix without it, which is shown cyan and the green dot lines, and compare against the HMON, which is the hunter green shown here. And on the right side, that's the maximum intensity for one particular cycle, which is 12Z on September 2nd. And the first 54 hours in all three simulations seems to be aligned with the best track in black. But the bug fixed HAFS, and without it, they are start to diverge against the best track and then HMON. So particularly the reason I brought up in HMON in this slide is that HMON uses the same HICOM ocean model for coupling. So what is happening here? Why the intensities are quite different? So next slide. So top two panels is showing 42-hour SSD simulations from HAFS on the left and then HMON on the right side, superimposed with the predicted tracks in the black dot lines. And then you can see at the surface, you hard to see differences at the 42 hours. But the bottom panel, that's the vertical section of the temperature field, and along with storm centers in the time in the vertical lines. Okay, so this is animation from the 0 to 126 forecast hours, shows that how that the upper layer changes when the storm is moving around. So it's a HAFS on the left side, that is a total excursion distance of 126 hours for HAFS on the left, which is 800 kilometers from the original. And then on the right side, the HMON, the storm is extending almost 1,300 kilometers, excurse 1,300 meters, which means, HAFS storm is pretty much stay within a 2 by 2 degree area. So that means, storm is going to have a higher chance contact and longer contact period with the ocean model. Okay, next slide. So top two panels is showing the largest scale of the HAFS on the left and the HMON on the right side at the 850 hectopascal, or with the absolute vorticity on the left and the relative vorticity on the HMON in the shaded, and the contour lines represented by geopotential height, DAM units. And so when you look at the top two panels in larger scale, not much difference. Okay, so Daniel stay positioned at the center of the domain and the next to extratropical cyclones, which is much bigger, about interacting each other, very close each other. And the bottom panel shows as the relative humidity at the 700 hectopascal for HAFS, left one, H1 in the middle, right one in the HFIP for comparisons. So what this particular bottom panel shows is HAFS predicted a lot of moisture latent TC environment compared to H1 and then HFIP. Next. Okay, so just take a look at the initial SSD conditions. HAFS on the left and an encoder, which is Navy analysis product in the middle, and the right one is the differences in SSD initial conditions. But in the bottom panel is HAFS at temperature simulations against the observations, two Argo observations, these two, and Argo observation is in a black curve, and then HAFS or HICOM temperature profile is the cyan. So as you can see that mixed layer depth is substantially overestimated, especially on the 390, 12, 19. The mixed layer depth is about 50 meter, but the observation tells us it's about the 20, 25 meter. So this one represents that the ocean, upper ocean contains a lot of heat potential energy. Okay, next. So this is a good, perfect recipe for intensification. Okay, storm is moving. The ocean underneath is very warm, thick layer, and then TC itself has a lot of moisture inside. So this is perfect recipe for the intensification. That's how we saw in the Daniel. Next. Okay, so, conclude. Oh my God. Okay, so in the past 2 years, we do have a lot of ocean observations through the different programs like UGOS, IUS, or in a GOMO, Extreme Event of Ocean Observation Program. So we do have lots of in situ observations. So how do we use these observations? So we have to make a more routine exercise of ocean validations, including against these observations. That's what I'm saying. Next one. So this is one example of during the Fiona against the glide observations and the temperature section in the color contour lines on the observation on the middle left, and then simulations on the right side. And the bottom panel shows that the temperature at the 10 meter water temperature in model in the orange and the observations black. So that there is definitely discrepancies in the ocean, upper ocean model structure there. Next. And this is another example of the water temperature and the salinity against the Celadron observations during the Eon. Next. And we do also have the WSRA wave and the surface roughness observations during the Ion. So we do have a lot of observations in place, but we need to encourage to set up the routine exercise of ocean validations. Okay, this is a lesson learned that I from the three-way coupling, and then usually the CD has a different distribution, which is a TC quadrant dependent CDs. But based on these studies, I found that there is no quadrant dependence on the CD, which is on the bottom panel of the contour shaded plots. Okay, so it turns out that what happened is that we didn't use the surface roughness coming from the wave tree directly. Somehow we do have scaling it based on the wave tree roughness before we send it to the atmospheric surface boundary layer. So this is one lesson. We should get away from this approach, ratio approach. And the next one. And then three-way coupling, there is a substantial impact on the ocean side as well. So, okay, so there is energy shift with or without wave coupling toward the geostrophic scale, which is inverse geostrophic turbulence cascade. In other words, you can all have all the energy, wave energy goes into geostrophic balance. And the second middle panel is the SST cooling at the different radius along the storm locations, showing that three-way coupling, which is on the left side, has a substantial SST cooling compared to two-way coupling on the right side. And the last set of figure, which is mixed layer depths along the storm track. Notice that Caribbean Sea and also loop current has a substantial mixed layer depth compared to two-way coupling on the right side. Next. Conclude, next slide. Okay, so we currently have a bulk peaks on the NUAPSI cap, but we'd like to have more bulk peaks on the sea depths. And the next one is, again, we have a lot of in-situ observations in Oceanside. We like to promote a website so that we can do ocean verification routinely. And the last one is everything is, making effort to build the Earth system modeling, which have to have a better realization of air-sea interactions and the improvement of a marine boundary layer. And the last two items is about the plan for HAFS version 2 and version 3. Thank you.
Yeah, this brings, this was the last presentation of the session. And thanks to everyone who presented and giving thoughts to what we are going through and inputs. Thank you very much for everyone, to everyone for attending these sessions. One more request I have, there were so many interesting results here, which are fast maturing. We have monthly seminars, HFIP seminars. We do that because it's in the best interest of HFIP as well as people who want to put their work forward. So please go ahead, sign up for these seminars from time to time, and please, it's because of your work that we sustain these seminars actually, and thank you for doing that.
Yeah, we won't have the seminars in December or January because of holidays, AGU and AMS. But with that, it's time to break for lunch. The sponsored lunch is a Mexican buffet. It's in the same place as yesterday. For those of you online, again, sorry we can't feed you. We only have an hour today for lunch, so please be back as close to 12:30 as possible so we can get started with Frank Mark's session that's after lunch that deals with observations.